Hello viewers, hope all of you are doing great. I just have finished editing a 4 hours long comprehensive video on mathematics of neural network. In this video, I'll guide you through the entire process of deriving a mathematical representation of an artificial neural network. I'll start with a bare basic sketch of an artificial neural network, and I'll proceed step by step, starting with the labeling of the weights and the biases of the network, till the final mathematical equations that describes a neural network and its operations. In this process, we'll get a lot of insight into the different concepts involved in a neural network, such as what does a neuron do? What is an activation function? What is forward pass? What is cost function? What is the optimization of a cost function? What is gradient descent? How do you compute the gradient of all the weights and the biases in a network using the chain rule of partial differentiation and the backpropagation algorithm as a whole? Also, we'll be learning about what are hyperparameters, specifically what is this learning rate and what is this epoch. So if you're someone who wants to understand the math behind an artificial neural network, or who wants to understand how a neural network works in its core, or you are someone who wants to implement the neural network from scratch, then this video is certainly for you. As I said, I'll be taking you through the entire process step by step. For that reason, this video is a bit longer, so that I show you all these steps of derivation. However, for some reason, if you're interested only in the final equations or the representation of the network, then you can skip the video till the end, where I did a summarization. I showed you the final representation and a very small or little explanation of that representation. Having said so, now it's time to start. Although the math that we are going to derive today is for an artificial neural network in general, but then also to carry out the discussion, let's assume that this is the artificial neural network for which we want to derive the math for. At the end, you will realize actually whatever the math we will have at the end, it really doesn't matter whether we have 3 neurons in a layer or we have like 300 neurons in that layer. And also you will realize that it will be only a matter of few adjustment there, or only a matter of writing a few more equations of in the same pattern if you want to increase the number of layers in the network. So you rest assured that if you understand the derivation of the math of this specific network, then you basically understand the derivation of math for any network, where in layer you can have any number of neurons, and then in that network you can have any number of layers. So this is sort of the minimum example where and in this minimum example you will find all the possible cases that we have to take care of when we are deriving the math for an artificial neural network. So in this network, what you can see is that this network takes 2 inputs, and then we have a layer here that we call as the hidden layer, and in that hidden layer we have 3 neurons, and then we have another layer where we have 2 neurons, and this is the final layer in this for this network, and whatever it is the output of these 2 neurons, that will be considered as the output of the network. So in general, what this network is doing is it is taking 2 numbers as input and it is generating 2 numbers as output. Okay, now let's see what each neuron is doing. Okay, and you might be thinking at this point that I have actually prominently keeping these weights and these biases. I have not labeled them. It's prominently visible that these are sort of blank there. I should have labeled them properly. And yes, I kept them blank for the time being because I want you people to realize that if you level these weights and biases in a systematic way, that helps you deriving the math very easily. Okay, so I can label them as anything, right? W1, W2, W3, W4, B0, B1, B2. In any way I want, I can label them. But the thing is that if you do it in a systematic way, then it becomes very much aligned with the math that you are doing. I mean, doing the math becomes very easy if we follow some pattern while labeling these weights and biases. And that's the reason that I'm keeping it blank for the time being. Before actually putting the labels here, let me just take you through what each neuron is doing internally there. Okay, you know that, but then also just to make sure that we all are on the same page. So you can see here inside this neuron, what I did is like I wrote something like Z is equal to this, I wrote something like Z is equal to, summation. It's just a shorthand notation to, I'm writing here in a shorthand notation just to tell you people that, okay, in this neuron, and then I wrote like this bar there, and then I wrote something like activation, and then this G. Now, what this thing means is that, okay, this neuron is first, this neuron computes an intermediate result. Let's call it say Z. And what that intermediate result is, I wrote it like only the sum, but it is actually the weighted sum of its inputs and added with that a bias. Okay, so I'll be coming to that point. But the thing is that what you should realize at this point is that this neuron is computing first this intermediate result G, which is nothing but the value of this neuron multiplied by the weight on this line, then the value of this neuron multiplied by the weight on this line, plus this bias there, and whatever it is, that is this Z. And now you realize that now Z is a scalar number. It's just a number there. Like say, for example, it might happen that Z is equal to 5.9 based on these weights and these values there. Okay, and once that number is calculated, what the neuron does is it passes this number through an activation function, or you can think it of like this is a function. Activation function, we call, basically what it does is that it computes the Z, and then it passes that Z through a function, and whatever it is, that function, we call that function in terms of neural network as the activation function. Now see, in an artificial neural network, you can use different functions as activation functions, but one very common requirement is that these activation functions should be non-linear. Okay, non-linear in the sense that the output of the function, say for example you are giving input G, then the output of that function should not linearly depend on this Z. And this is a very this is a very essential requirement there. I mean, we are not this is not some fancy mathematical operation we are doing here. It is a very crucial and important mathematical operation that we have to perform here. That is, without this non-linear activation function, artificial neural network would not have been possible, at least for many cases. Okay, it means you can say like an artificial neural network would end up in doing only some trivial tasks, not these very complicated tasks like the way they do things nowadays. You can see, right, they are very good at recognizing face, they are very good at recognizing objects in an image, and not only that they can generate images, not only that they can understand language, not only that they can write programs, and all these things are possible. I mean, all these things would have been impossible if we do not have this non-linear activation function sitting there in each and every neuron there. Not each and every neuron there, but for most of the neurons there. Okay, that's a side note that I wanted to tell you people. So what basically this neuron is doing is that each neuron is doing, you see here, the same operation is being performed by all the neurons. I have written here basically the same thing. Z is equal to the summation, weighted sum of this input. Like basically how you interpret it, Z is equal to summation. It means like it is the weighted sum of its inputs, and then plus this bias, and whatever that Z is, it passes that Z through some activation function. And this neuron is also doing the same thing. This neuron is also doing the same thing. It is also doing the same thing. It is also doing the same thing. Yes, although they are doing the same operations, they are performing the same operations, but one thing you realize that they're performing the operation on different weights and inputs there. So for this neuron, these are the inputs and these are the weights and this is the bias. But for this neuron, although the inputs are same, weights are different, bias is different. For this neuron, these three are the inputs and these three are the weights and this is the bias. And for this other neuron, it has the same three inputs as this neuron has, but it has different set of weights and then different bias, right? So it means in general, although all these neurons are more or less doing the same thing, but they are doing they're performing those operations on different set of weights and biases and inputs. Clear up to this point? Yes. Oh, okay, great. Now let's move to the important step. Now it is time to label these different components of the network. By component I mean these different weights and biases and some intermediate results like this Z properly. Okay, let's now label them properly. Now you see, okay, to start with, let me first label this very abstract thing which we call as the layer. Okay, so the input, these inputs, like see here, these two small circles there, although we call them like the neuron of the input layer, or although we call these as an input layer, that is basically not a layer. I mean, that's or you can say like that is the layer that receives the input directly from the user. I mean, see here, this small circle is, these two small circles are different from these five big circles, in the sense that these two neurons are not computing anything. Whatever their output is, you see here, these are the output, like it is forwarding some output certainly, and those outputs are basically the inputs that the network receives from the user. So they do not do any computation internally. However, for all these big circles, you can see that okay, all of them are computing this weighted sum, passing it through some activation function, and that operation is being carried out by all these different neurons. So in that sense, you say like, okay, this is not actually a layer of the network that learns something. It is just the input layer that receives the input from the user. So although it is the case, what we'll be doing is we'll be labeling this particular layer as layer 0. In computer science, we know like we always start indexes with 0, and here if we call this layer as layer 0, you will realize in a moment that it becomes very useful when we derive the math. Okay, so you call it, say for example, level 0, and then I'm saying level, or no, actually I mean layer, layer 0 or level 0, it's okay, fine. Layer 0, this is layer 1, and this is, say for example, layer 2. Okay, so these are just the layers. This is the 0th layer, the first layer, and the second layer. And now let's try to give names to these neurons. Okay, now what I'll be doing is that I'll be calling these neurons, say I'll be giving a label to this neuron, say for example activation 0, A0. Okay, I'm writing it as A0. A stands for activation. Okay, activation 0. So this is like activation 1. Now, it is, you don't think that it is the name to that neuron. It is not that. It is the value or the output of the neuron. So output of this neuron is A0. And you might be thinking this neuron is not computing anything. So from where that output term is coming? So whatever it receives as input, that only is the output of this neuron. Okay, basically A0 is nothing but it is, it is the 0th component of the training example there. Okay, so that way you can think it out. But anyhow, in general, we'll be calling it like A0. It means the activation 0, activation 1 of layer 0. Similarly, the output of this neuron, I will be labeling it as activation 0. And output of this neuron is activation 1. And output of this neuron is activation 2. And similarly, here also, like output of this neuron, we'll be calling it as activation 0. Output of this neuron will be calling as activation 1. Now you might be wondering, okay, there are like 3 activation zeros there. How do you distinguish one from another? Yes, that's a valid question. We want to distinguish one from another, and how we'll distinguish them by putting a superscript on all these levels. Say for example, we say this is the activation 0 of, or you can say this is the activation of the 0th neuron, activation of the 0th neuron of the first layer or the 0th layer. So activation 0, superscript is 0. This is activation 1, or this is the the activation of the first neuron. I mean, the neuron at the first index of the 0th layer, like that. So here now you know what it will be, what will be the superscript here. It will be the superscript 1. It means it is the activation, 0th activation of the first layer. It is the first activation of the first layer, the same layer, and it is the second activation of the first layer, like that. Similarly, it is the 0th activation of the second layer. It is the first activation of the second layer, like that. You will interpret it. Now, before proceeding further, let me tell you one thing here, that this convention, this way of naming these weights and biases and these layers, certainly this is not something that I discovered, or it's not my contribution. Certainly, what am I doing is I'm following the notation which are followed by at least a large community there. Like, for example, if you follow the tutorials of Professor Andrew Ng from MIT, then you will see he uses this notation. Another reference I can tell you is the book. A very good book is there. Like, if you are a beginner who is trying to understand neural network or deep learning and all these concepts, then, and you are looking for a very good book, then I can tell you there is this very good book. I have it actually. This is a free online book, but I got a PDF version of it. I did a printout of it, and the name of the book is, can you see that? I'm not very sure, but the name of the book says like Neural Network and Deep Learning by Mitchell Nielson. I'll provide you the link of this an online version of this book, and in this book also the author follows the same way of leveling these weights and biases. So that was something that I wanted to tell you. Like, you just do not need to feel that these way of doing the thing is somehow I am picking up randomly or something like that. It's not that. It is followed by many community. It is followed by like a great by at least a good fraction of people there, and whom you follow, or whom we all follow more or less, when we try to learn the thing. So you will be in a very comfortable position. Like, if you understand it this way, then you will find the same thing or the same notation in some other well-known resources also. So you don't need to worry about it. Okay. But also at the same time, you make it clear in your mind that this is not the only one way you can represent, or you can write these, you can label these weights and biases. Different authors prefers different their own ways of doing the thing. So if you see suddenly some other type of notation, don't get confused. Okay. But one thing is for sure, that once you understand the underlying working of the network, or the how all this math is working, and how you can derive the math and everything, then you can easily switch from one notation or one way of writing the thing to another way of writing the thing. So you will be very much comfortable. Okay. Great. Then, so where we were like, we just finished leveling these activations. Okay, like, we now say, like, this is the 0th activation. This 0 is the 0 index of the activation, and this superscript 0 is the index of the layer. This 0 is the index of the activation, and this superscript is the index of the layer. Clear? Great. Now let's move to the next part. Like, here we want to now label the, say for example, the biases. Okay, then now let's try to give names to these to these biases. So now this bias is let's call it, say for example, bias 0. Now, you might be thinking, why didn't I added any bias here? Because you see here, as I said, no, these are directly inputs there. I mean, this A0 or this A1 from this 0th layer, they are directly the input, and they are not the output of any computation. So since these neurons are not doing any computation, so there is no question of having them a bias there. However, for all the other neurons in the network, all of them will have their own individual biases. Say for example, this neuron has has its own bias like B0, this neuron has its own bias say B1, this neuron will have its own bias say B2, like that. And similarly, this neuron has also its own bias say B0, this neuron also has its own bias say for example B1. Okay, and again, since there are two B0s now, we have to distinguish it. This B0, this B0 is the bias of the zeroth neuron of the first layer, you see, of the first layer. So we'll be writing this superscript to distinguish the biases from one layer to another layer. So this is B01, it means this is the zeroth bias of the it is the bias of the zeroth neuron from the first layer. It is the bias of the first neuron of the first layer. It is the bias of the second neuron from the first layer. Same thing here also. Now it is the bias zeroth means it is the bias of the zeroth neuron from the second layer, bias of the first neuron from the second layer, like that. So we have given name to all these different biases also. And what is left then? Then these weights. Okay, now let's see how we can give names or how we can label these weights there. Now you see, okay, let's represent weight by obviously W intuitively, then W, and you see, okay, let's see these things. These two lines which are coming to this neuron here, these two lines here, this line and this line, these are weights there. Okay, they represent some real number that we call in terms of neural network as the weights there. Okay, and see, these two lines are the weights which are associated with this neuron. What I mean by this is okay, the way this B0, B0 is the bias of this neuron or bias attached to this particular neuron. In the same way, you can think of these two are the weights which are attached to this neuron. Similarly, these two are the weights which are attached to this neuron, and these two weights are attached to this neuron. Here, if you see, this neuron has three weights there, and this neuron also has three weights attached to it. Okay, so you can think like, okay, now the way this bias is the this bias term is the term of this neuron specifically. The same way these two weights will be the weights of this neuron specifically. Understood? Okay, now let's give them name. So what do we want to this weight is the weight of the zeroth neuron from the first layer or of the first layer. You can say it like this. This weight is this particular line, or this weight is the weight of the zeroth neuron of this particular neuron from the first layer or of the first layer. So that's why I'm writing this superscript as 1 and this 0. Okay, that's fine. But the thing is, that way, if I have to give name, then this weight, what will I call it? I will call it this way. This weight is also the weight of the zeroth neuron, right? Because this is also the weight of the zeroth neuron, and it is the the weight in the first layer. So it'll turn out that both these names will have, they will become the same. But there is one, where is the difference between this weight and that weight? The difference is that from where this weight is, or to which neuron of the previous layer this weight is connecting this neuron with. It means, okay, this particular weight is the weight of the zeroth neuron, but from which neuron of the previous layer it is coming into this neuron. So it is the zeroth neuron of the previous layer, so you'll write it in this. Okay, it is the zeroth neuron. Similarly, this weight is the weight of the zeroth neuron of the first layer. That is fine, that's okay. But the thing is that this weight is coming from the first neuron, the neuron at index 1 from the previous layer. So we'll be writing it like, okay, this is W01. That is how we interpret it. And if you are reading that book that I just showed you, and for which you'll get the link in the description, there you will you'll get the same notation. So following the book will be not very difficult for you once you understand this notation. Okay, and also following Andrew Sir's lectures will also be very easy once you understand this notation. Understanding this notation is the first step to understand the math behind artificial neural network. Okay, great. Okay, then using the same approach, then let's try to give name to this particular weight. The name of this weight will be then or the level of this weight will be, then it is the weight of the first layer itself. So the superscript is 1, and it is the weight of the first neuron, or the neuron at index 1. So I'll be writing 1, and this particular weight is coming from the 0th neuron of the previous layer. So I'll be writing here a 0. So it means it is the weight of the first layer, and this weight is the weight of the neuron which is at index 1 of layer 1, and that weight is connected with the 0th neuron of the previous layer. So previous layer means if the current layer is obviously 1 here, so previous layer is 0. Okay, so the same way, how will you give it? How will you give the name to this weight? You will give it like W1, and then it is the weight of the first neuron coming from the first neuron of the previous layer. This particular weight I'm talking about. Okay. Similarly, how will you give it? Okay, let's write it. So this particular weight here, this weight here, will be writing as weight of layer 1, and it is the weight of the second neuron. See, neuron at index 2 coming from the 0th neuron. So 20, and then this down there, this particular line, you will write as it is the weight of the first layer of the second neuron, or the neuron at index 2, and coming from this weight is coming from neuron 1, or neuron at index 1. So I'll be writing as 21 there. Now using this same idea, let's label all these weights here. So it will be W weight of the second layer, so W2, and then it is the, I'm talking about the weight of the 0th neuron of the second layer, so 0, and this line is coming from layer 1's 0th neuron, so 0 here. Now same thing, this W2, it is of the neuron 0 itself, the same thing, the 0th neuron, but it is coming from the first neuron. So this is 0, 1. And similarly, this weight will be the weight of the second layer, certainly, and it is the weight of the 0th neuron, certainly, and it is coming from this third neuron, that is neuron at index 2 from the previous layer. Okay. Similarly, this weight here will become W2, and this is the weight of the first neuron, so 1, and then it is coming from 0th neuron of the previous layer, 1, 0. W2 1 1, this particular line I'm talking about, and this line here, or this weight here, it will be W2 weight of the second layer of the first neuron, or of the neuron at index 1, and it is coming from the neuron at index 2 from the previous layer, so 1 2. You see here, this neuron has 3 weights, and all the 3 weights are starting with 0 0 0. These are the 0th neuron weights, W1 0, and so this, all of them are W1 1 1. It means these are the weights of the first neuron. However, this one is coming from the 0th neuron of the previous layer, this one is coming from the first neuron of the previous layer, this one is coming from the second neuron of the previous layer. Same way, you can apply the same concept here. They see here, these 2 weights are the weight of the 0th neuron here, so W0 W0, but this one is coming from 0th neuron of the previous layer, this one is coming from the first neuron of the previous layer. Similarly, these 2 weights are the weights of the first layer, so W1 W1, and then 0 and 1. These 2 weights are the weight of the second neuron, W2 W2, and then it is coming from the 0th neuron of the previous layer, it is coming from the 0th neuron of the first neuron of the previous layer. So that's how we give names to these, or we label these different weights and biases. Okay, once you have understood this, then you can say like, okay, you have understood a great deal of the thing. Now things will make more and more sense now. Okay, let's see how we can use now, or make use of this specific way of labeling these weights and biases. Okay, for that reason, now let's concentrate on what each neuron is doing. Okay, what's this each neuron is doing here. So now let's now see the operation of this specific neuron. But before that, let me just do one more thing here. So here I'm just calling all of them as Z, G, and G, and then passing the Z through an activation function. All of them I have written as Z. So let's give them name, label also, like, so that we can distinguish one Z from the other one. So let's call it, say, this is the Z, 0th Z, or of layer 1. Obviously, that's following the same idea. This is the first Z, or Z at index 1 of layer 1. and this is the z or second z or g at 2. See, same thing. I mean, activation 2 of layer 1, similarly z2 of layer 1. Now see, these z's are intermediate results. They are like, we'll be using them certainly, but you know, in terms of the network, they're, yes, obviously they're the intermediate one. Okay, and then z, this is 0th neuron of the second, I mean 0th z of the second layer, and this is the first g of the second layer there. Okay, I guess now everything is fine. Now once we have that, once we have given name to all these different z's, then let's see what these single okay, let's first concentrate on this g0 there. Okay, like say for example here, what is this? Okay, what is this actually? You see, as I said, no, it is the sum, and it is the weighted sum. Okay, now this time let me write it in now in a complete way rather than simply writing it as this symbol sum. What this intermediate result z0 is, it is the weighted sum of the inputs this neuron receives. What is that weighted sum of inputs that this neuron receives means? Okay, so see, this z0, you can write it as, okay, the weight 100, this particular weight multiplied by this particular input, multiplied by input 0 of 0th layer. And then what it will do is it will add that thing with the same, now it will do the same thing with this other input also. That is, it will take this weight, W0, the corresponding weight is for, see here, this is the weight through which this neuron or this activation is connected with this neuron, or this activation. So the weight is W01, or it is the, the weight of the 0th neuron, which is coming from the first neuron of the previous layer, and this weight is weight of layer 1 multiplied by the, since it is coming from the first neuron of the previous layer is A0 and it is index 1. So that's what actually A01. See, I just wrote it without even looking at the diagram. So that is the advantage. Okay, and then what it will do is it will add then, see, these are the two inputs it has received. This neuron receives this neuron has these two inputs, so it has to take the weighted sum of these two inputs. So two terms are coming here, and then what we have to do is what this neuron will do is that along with these two terms, okay, let me write this thing also as multiplication. Okay, along with these two terms, it will add this specific bias. So what it will do is it will add the bias, the 0th neuron bias. See, this is the weight of the 0th neuron of layer 1 So similarly, the bias will be the bias of the 0th neuron of layer 1. So that is what this Z01 is. Now once that this intermediate result is computed, what it will do is the neuron, so yes, the neuron will compute this final output. This is the actual output of the neuron. And how that actual output of the neuron will be computed? The actual output of the neuron, or actual output of neuron 0, the activation of neuron 0 of layer 1 will become then the output of a function. I'm writing it here as ACT, activation function, and it will give this intermediate result Z0 of layer 1 as input to that function. And now this function, the function that I wrote here as ACT, this function is known as the activation function. Okay, each and every neuron will, most of them, okay, will have these activation function sitting there, or as the second operation after computing the weighted sum. Always they will do it is, they will pass that weighted sum through some activation function, and this is very crucial. Otherwise, if the task that the neural network is doing, if it has to do some non-linear separation in some way, and then it will be impossible without these activation functions. And when I say activation functions, you can have different functions you can use as activation function, but one requirement is that they should be non-linear, in the sense that this input, the output of this function should not depend on this input linearly. That is, you are not supposed to use, like, say, activation function like, suppose you just consider an activation function that receives an input x and it returns it returns say x squared. Oh, sorry, it returns say for example twice x. So in this case, it is not going to be a valid non-linear activation function, because whatever you are giving as input, it is just returning a linear somehow whatever the output it is returning, it is a linearly dependent on this input. So it's not going to be a valid non-linear activation function. However, there are like certainly different functions are there which you can use as valid activation functions. So most commonly used ones are like rectified linear unit, ReLU, and other one is say sigmoid. Okay, now you see here which one you use. So in general, so rather than like being very specific here, like what activation function that it is we are using here, I'm writing it in general. Okay, that is an activation function. That is a function that does some non-linear operation on the input, and whatever the input it is receiving right now for this activation function, it is just a single number. It takes that number, it performs that non-linear operation on that number, and whatever it is the output, it generates it as an output. So for the time being, to make things simple and general, what we can do is, instead of writing exactly one specific form of activation function, I'm writing it here in general like activation Z0. And believe me, you will not find any difficulty when we proceed further with this general name there. Okay, okay, just stay with me for that for the time being. Okay, great. Now we know now what this Z0 is and what is the corresponding A0 is. See here, from Z0, from Z0, we are that neuron is computing A0. Similarly for Z1, from Z1, see these are all like, I have to write it properly. Z0 of 0, first new layer. This is the Z0, sorry. This is the Z1 of layer 1, and this is the this is the Z2 of layer 1, and this is Z0 of layer 1, and this is, sorry, that's Z0 of layer 2, and this is Z1 of layer 2. Okay, so that is the actual, like I missed that point. Actually, I didn't name them properly. Okay, so anyhow, I think whatever it is that I wanted to convey to people, it is clear now that the Z's are intermediate result, and they are calculated as, first they are the weighted sum plus we add the bias there, the corresponding bias, and whatever it is this intermediate result, we pass it through an activation function. We means that neuron passes it through an activation function, and whatever it is the output of that activation function, non-linear function, that is the output of that particular neuron. Now, the same thing is happening for all these other neurons. So let me write them, like what is Z1 of 1? How many Zs are there? As many activations are there in this layer, that many Zs will be there. It's clear, right? So Z1 is, now we have to, now for Z1, we have to take care, we have to make use of the weights of these inputs are same, but the thing is we have to multiply them with the weights of that specific neuron, and we have to add the weight bias of that neuron in that expression. So we'll be doing it. So weight of the first layer itself, and but we're now this time we're talking about, instead of weight 0, I mean weights of the 0th neuron, we have to make use of the weights of the first neuron, and then coming from the 0th neuron of the previous layer multiplied by the, since it is coming from the 0th neuron of the previous layer, we have to multiply it by the the 0th neuron of the previous layer. This term is same, plus then weight of the first neuron, and coming from the first neuron of the previous layer, then we have to multiply it by the activation 1 of the previous layer, then we have to add the corresponding bias. So the corresponding bias is B1 of 1. It means this one, the B1 of layer 1. Okay, and you can see W111, this is this W111, and W110 is W110. It is multiplied by A00, A00, and W111 is multiplied by A01, A01. Clear? And then what we do, and from this G1 we compute A1. So A1, activation of the the first neuron and of layer 1, which is equal to passing through the same activation function, and we give here Z1 of layer 1. Same thing now we can do. What is Z2 of layer 1? Now we have to take care of, we have to make use of the weights of the second neuron, the neuron at index 2 of layer 1. Neuron at index 2 of layer 1 and coming from neuron 0 of previous layer. So we have to multiply it by neuron 0 of previous layer plus then weight 2 means weight of the second neuron coming from the first neuron and of the previous layer. So 1, then we have to multiply it by, since it is coming from this neuron of previous layer, so previous layer 0 and then neuron is 1. Then we have to add, basically see these three terms are the same, and then we have to add this corresponding bias. And what is the bias? Bias is B2 of layer 1. And then immediately the neuron will compute the activation. The corresponding activation is this A2 of layer 1, which is nothing but passing this intermediate result Z2 of layer 1 through this activation. That's all. So that's how these activations are computed. Now, in the very bottommost layer. Now, if you see it for a moment, what you will realize is that these operations, now see here, instead of now looking at the, instead of like thinking each neuron is doing these operations, you can, as a whole, you can think like what all the neurons, you can represent the operations of all the neurons in that layer in a single go, as a single thing. Okay, and if you look at these three equations there, you can see, okay, it is possible. Okay, now let me bring your attention here in these three equations, and let me draw a line here. Okay, like say for example, I'm just drawing a line to bring your attention to this part here, and then you just see this part here, and then this part here. Let's see this thing here, and this thing here. Okay, now what this Z0, Z1 and Z2 they're doing is, if you look at this part, it is, now you see here, this part you can write it in this way. So for example, you just assume that you have a matrix. That matrix has these components there, like 0, 0, and the name of the matrix is, say for example, W. So W00, W01, this is the first row of the matrix. W10 and W11 second row, and then W20 and W21 is the third row of the matrix. Okay, and then assume that you multiply that matrix. Let's say give this 1 also, if you want, you can give. So 1, 1. Now if you multiply this matrix by this vector, say for example the vector is A0, 0 and A1, 1. Okay, that is, if you perform this matrix multiplication, this one you can consider as like 2 cross 1 matrix, or you can consider it's a column vector where we have these two components there. Now say you are, now let's see what will happen, or when we multiply these matrix by this vector. Now what you can see is that if you multiply this matrix with this vector, you will end up that the result will be something like this. So obviously so it's a 3-row 2-column matrix multiplied by another 2-row 1-column matrix. So the output will be a 3-row 1-column vector, I mean like this, or matrix, whatever it is. 3-row 1-column, so some 3 components will be there, that like 3 rows 1 column will be there, and that's what you see here. And what will be this corresponding term here? This term will be exactly same as this one. You see, W00, W00, I mean this term, this much of this one plus this much of this one. This much of this one is like W001 of A00 plus W01 of A1. So W011 of A10. I mean this is 0. I just did it wrong. So the W11 of A0. This is the term, and this is exactly same as this. W001 into A0, A0 plus W011 into A1 of 0, A1 of 0. Right. And similarly, now you can fill it up like this one. This term will be same as this expression, and the value of this particular value will be same as this expression. So this thing you can simply write like, if you have a, now if you have a like matrix whose name is, say for example, W1, which is this matrix, then what you can think it of is that this operation is nothing but multiplying that matrix with, what are these A zeros and A ones are? These are nothing but the inputs that the neural that the network received, or you can think it of like, these are the in general, what you can think of is that these are the activation of the previous layer. Right? If you are computing the value for layer 1, then A0, A1 represents the activation of the 0th layer, which in this case is the input. But in general, these are the activation of the 0th layer, right? So what you can think it of like, okay, and see this weight matrix here and this matrix W here. The rows are not randomly written. You see, the first row is W00, W01. This is the pair, of the these two are the weights of the 0th neuron. You can see that W00, W01, this is W00, W01. So these are the weights of the first neuron, these are the weights of the second neuron, and these are the weights of the third neuron. See, these are the weights of the first neuron, second neuron, and the third neuron. So as many neurons as you have in that hidden layer, that many rows will be there in this weight matrix. That makes sense, right? You can think it of like what in other sense, in terms of linear algebra, like just one interpretation, one way of interpreting it, this matrix multiplication, as each weights there, like each row there, you can think it of like, they represents a combination, that represents a specific combination of the input. You can think it of, if this is the input, then these combination, if you take of the same input, then you will get this output. Then if you take this other combination, then you will get this output. And if you take this combination of the same input, then you will get this third output. So if you need here, say for example, here you want to generate like 5 different combinations, then you will be writing here 5 different rows there, because each row represents the weights associated with each combination there. Are you getting what I'm trying to say you? Yes. Okay. Then it's fine. Now, just to summarize, you see here that is the advantage of when I said that leveling the weights and biases in a systematic way helps you derive the math, and that now you can see that's directly like coming into place now. Like see, W00, W01, the first row represents the weights of the first neuron of layer 1. Second row represents the weights of the second neuron of layer 1, and this third row represents the weights of the third neuron. See, W20, W21, W20, W21, these are the weights of the third neuron of layer 1. So that's what we can represent. And then these activation, this column vector is also like not some random numbers or random vector I have written here. These are the the activation from the previous layer. If it is like A0 and A1, then it is A00 and A1, means A0 of 0th layer, A1 of 0th layer. So basically what the point is that if we multiply what is the point is that in each layer now, in the weights of each layer we can represent by a matrix. So let's say all these weights we can write, or we can put inside a matrix. Let's call it say W1. And these activations we can represent by a vector, say activation 1. Okay, see, I just removed that superscript and subscript. Subscript, I removed that. It's not when I say A1, you think okay, it is the vector. Okay, it has some components, A0 component, A1 component, based on how many neurons you have in the input layer. Okay, and these W1 now is in general, it's a matrix, and it depends on like how many how many neurons. See, the size of W1, it depends like how many rows will be there in that matrix. It is same as how many neurons you have in that layer. If you have 3 neurons, you will have 3 rows there. And certainly it will have how many columns? It will have as many columns as the the size of your input, because rows, like if like 2 rows are there, then sorry, if you have 2 columns here, so certainly it should have 2 rows there, right? You got it? I guess the people got it now. Now, okay, now the same way, if it is the case, then we can represent all these biases also. You see, in the same go, you can think it of like all these biases, then we can represent simply by writing this term B, and we can say, okay, now B is not a single scalar number, it's a vector, and it is that contains all the biases of layer 1. All the biases of layer 1, these are all the weight, this is a matrix, all the weights of layer 1. This is again a vector or column vector that represents all the activation of the previous layer. Similarly, the activation of this layer, then you can represent simply as A1. I mean, when you say like A1, it is without any subscript. Then you say, okay, this is the this is the column vector that has where each component represents the activation of the corresponding neuron in that particular layer. See, this activation is of layer 1. These are all layer 1 term. W1, this weight is it is associated with layer 1. These biases, they are associated with this layer 1, or this activation vector, it is also associated with layer 1. However, this one, why did I do that mistake? I'm sorry. This is A0, huh? Okay, this is like activation of the 0th layer. Okay, I'm sorry, where did I do that mistake? Don't mind it. Now, but then also, even if that you can tolerate that small mistake, like it's still, we are still like consistent with our argument, right? So this is the activation of this vector represents the activation of the 0th layer, and these weights of the first layer, biases of the first layer. This is another vector that represents the activations of the first layer there. So similarly, if it is A1, then you can say now, okay, now there is no big deal there. There's all these weights you can represent as W2, and then you can represent all these biases of layer 2 as B2, and then all these activations of layer 2 as A2. Does it make sense? Now see, this A2, you don't think like it is a single number or scalar. It is a vector that consists of all these the activation of that particular second layer. Okay, up to this point things are clear? Then don't worry. Now again, take a deep breath and let's proceed further. Now see, again, I'm moving very slowly, and for some people it might be like as soon as they see the picture, it might be very clear in their mind that okay, that's what is actually happening. It depends like how much time you have previously spent with this with linear algebra and with all these notations. So I'm assuming like if someone who might not have that much of exposure in the past with this linear algebra thing, and even if they had, like suppose due to the lack of interaction with that particular area, they might lost all their context and all. So for those people also, so that this video becomes useful, I mean, I'm keeping, I just want this video to be useful for everyone. Okay, so if it is quite straightforward for you, whatever it is that I'm telling you right now is okay, no problem, and then you can directly, as I said, no, you can skip now, because if this thing is quite straightforward at this point, then like what is coming next and all, so you can directly skip to the last, and then you can see the formulas, and from there you can proceed with the implementation. Okay, and that's all. Okay, now what we're doing is that, okay, now we have represented it. Now let's come back to this point. Now what we know, okay, W1 is this, and activation, so this is your W1 now, and now this is your activation 0, like in this diagram, whatever this activation 0, and then bias is like it's a vector B0, B1, B2, like that. And okay, the bias is also is important, right? I mean, what we did is that these matrix multiplied by these activations gives you this part, right? Then what about these biases? As I said, no, biases also you can represent as a vector. So let's do it. Now what we have realized is that this part is, as we said, this thing is nothing but weight matrix 1 multiplied by activation 0. This entire thing can be written it like that. And this B0, B1, B2, it can be represented as I showed you there, like all these biases we can represent just by a vector. So let's call it this vector B1. This is B1 vector, right? So ultimately, then this z's also you can write as a vector. So ultimately what we can do is that we can write like z, the intermediate result of layer 1 or any specific layer, say in this case layer 1, is equal to what then? It is nothing but the weight matrix of that layer W1 multiplied by the the activation of the previous layer, that is activation of the previous layer, and added with that is the bias of that layer. So weight is layer 1, you're computing z1 of layer 1, and you have to add the bias of layer 1. So this is z. I mean, this thing is now not a single number. I mean, if you do this, like multiply this weight matrix by this, and then you add this b0, b1, b2, ultimately you are going to get these three numbers there, right? So that three numbers, if you put it inside a vector, and that vector I'm calling is as z1, it will have these three terms: z0, 1, z, I mean this zeroth index, the first index, and the second index. I think things are clear now, right? Okay, great. Now once you have that, then what about this then? That thing also, again, you can write it like, now my activation vector a1 of layer, I mean activation vector a1, that is activation of layer 1, you can think it of now, it is you, as if you are now passing this entire vector z through this activation function. So what this activation function will do is, basically you can think it of like, when you do something like this, you can think it of like, this is the same as, like, see, suppose you just consider this z has different components. Say this is z1 of 0, then z1 of 1, then like that it can have like, say, n x k, whatever number of components. Say for example k components. In this case k is equal to 3, means we have 3 components, so this k will end up at 2, but in general I'm writing, say, this one. Okay, so in that case, when you do this, like you pass that vector through this activation function, you can think it of like, that activation function will operate on each component of that vector individually. It will operate on that each component of this vector individually, and it will generate a term. Now see, activation of z0, it will be a term. This will be another term, this will be another term. That term will be, actually, see, what is this activation z0? Activation z0 of layer 1, activation z0 of layer 1 will give you activation 0 of layer 1, right? And that's what, actually, it's activation 0 of layer 1, it is activation 1 of layer 1, activation 2 of layer 1, and if you represent it in the form of vector, you get this a1 vector. And as you can see, a1 vector has all these three terms there. Okay, understood? Okay, understood. So let me just, so what you just have understood is is tremendous, actually, right? I mean, now all these operations, instead of thinking them like, each neuron is doing that thing, now you can think of like one level up. Now you can think of layer wise, right? I mean, multiply the weights of this layer with the activation of the previous layer, add the biases of this layer, you get the activation of the current layer. Then you do the same thing. You just activation of this layer, multiply with the weights of the next layer, and do all the same operation. You get the value of the next layer, and the next layer, and the next layer. So this time, instead of this mathematical representation helps you think not in terms of these neurons now anymore, in terms of layers now as a whole. So in that layer, how many neurons are there? It is irrelevant now, right? Okay, great. Okay, let me now summarize the thing so that we can proceed further again from that point. So let me bring this diagram below. Okay, we have reached this point now where, as I said, no, you can think in terms of layers. Now see, okay, so what we have here is that like this activation 0. Now you should realize that in this neural network, now you can represent in this way. So this neural network has something called as activation 0, which is a vector. Okay, in this case, let me write down the sizes also. Okay, so activation 0, which is a vector or a column vector. In this case, you can see the size is 2 cross 1. 2 rows are there, 1 column is there. Okay, and then what we have? Then we have a weight matrix W1 whose size is what? How many rows and how many columns? As many rows as the number of neurons in the hidden layer. So we have like 3 rows, and we have in each row we have 2 columns because it is taking the weighted sum of 2 inputs there. So in each row we have 2 columns. So that is the size of W1, which is this W1. Then also we have this B1 there, B1, this is B1. And what is the size of B1? It is just like, as many hidden layer or as many neurons in your that hidden layer or in that layer, that many biases you need. So it will be like, say in this case we have 3 neurons, so 3 cross 1. All right, done. Then what will be the then this w2? W2 is again, okay, before w2 let's write what is this a2. Okay, so a2 is I mean, sorry, what is this a1? A1 is the activation of this layer 1, which is nothing but you know, it should be a matrix of like 3 cross 1, 3 rows 1 column. A1 has should have 3 rows 1 column. But you see here, this a1 we don't define by ourselves. It is the result of the operations of the network. However, this a0 we have to define it, like it is outside the network, right? I mean, it depends on like what is the size of what is your input size, or what is the dimension of your input. If it is a two-dimensional input, then it is 2, the vector will be of size 2. But suppose you just assume that you are trying to perform this handwritten character digit classification task. It's a ABC, hello world program in machine learning, right? So you most probably people have heard about it, where we have 28 cross 28 images. So ultimately that 28 cross 28 is 764, I guess. So then the inputs are of 764 dimensions. So in that case, you will have activation 0 to activation 763. So in that case, it will be a vector of like 764 cross 1. Got it? So okay, that's one. And this we have already, and this w1 is a parameter of this w1 represents the weights of the first layer of the network, and this is network parameter. And we initially, when we start training the neural network, we will assume this w1 to have some random values. So these we have to give initially to the network. Similarly, this b1 also we have to give initially to the network, maybe with some random values, but these we have to give to the network. However, this activation 1, this value, these values will be computed by the network by itself. Okay, and again, then we also have to specify the network, like we have to give the network, when we start the network, training the network, we have to give this under matrix w2. In this case, for this specific example, you just try to figure out what is the size of w2. So w2, first thing is that how many rows will be there in w2, and that depends how many neurons are there in that layer. So in layer 2, you see, this is their layer 2. In layer 2, how many neurons we have? We have 2 neurons. So obviously it will have 2 rows then. And then how many columns? Columns are like from how many neurons it is getting its input. So each neuron here is getting its input from 3 neurons from the previous layer. So its column size will be like 3, w2 cross 3. Okay, and then we need to have these biases. So biases means like it depends on like how many biases will be there in layer 2, 1 and 2. So the size of like b2 is a vector, and the size of this will be like 2 rows 1 column. And finally, based on this w2 b2, it will generate this final layer activation 2, which will be of size. Now what we want, like first look at the size here. How many values we want? We want 2 values, right? So certainly we know we want the size for this network, we want the size to be 2 cross 2 rows 1 column. And see, we know like this activation 2 is going to come from the multiplication of this matrix by this vector. Here also it says the same thing. I mean, sorry, not by this matrix by this vector, this matrix by this vector. See, w2 into 1, you see somewhere I wrote, no? See, w into, see, weight matrix of that layer multiplied by the activation of the previous layer. So in this case, it will be 2 into 3 multiplied by 3 into 1. So ultimately 2 into 1. So 2 into 1 negative. Okay, and out of all these, this is the network, this vector the network will compute, but this a0 is the input to the network. These weight 1, b1, these are the weights and biases of the first layer, weight 2 b2, weights and biases of the second layer. If you have a third layer, then you will have another weight matrix to represent the weights of that layer, and another bias vector that will to represent the biases of that particular layer. Clear? And once we have that, then how do we do? Now see, once we have this thing, now see one thing again, I'm telling you that when we start the network, we assume that these values are already there. I mean, we have a matrix called W1 that represents all the weights. Although we do not know at the beginning what are the exact weights, but we give the network the starting point, like some random weights there, some random biases there, some random weights again for layer 2, some random biases again for layer 2. Okay, these we give to the network, and then the network receives this A0 as the output, and the task of the network is to produce this A2 vector as the output. And then what operation we perform on neural network? Then the first operation, then we are ready now. Now we can represent the forward pass of the network just by, in terms of like, some matrix operation. Now, since, as I said previously also, that now you're allowed to think in terms of layers rather than thinking in terms of neurons. So for that reason, what you can do is that, okay, what is that forward pass? In the first go, the first layer, what it will do is first you compute. You first compute, say, the intermediate result z0 or z vector of layer 1 which is equal to whatever the weight matrix multiplied by the activation of the previous layer. So activation 0, I mean none of this w1, then you have to add the biases of this current layer b1. That's your z1 you do. And once you do that z1, what you do is then from there you compute the actual activation by passing this z1 through a non-linear activation function. So you now are ready to compute activation 1, which is nothing but if you pass that vector z1 through an activation function, and you see here this activation function is going to act upon each and every component of the vector independently, producing equal size vector as the size of this z vector, right? So it will give you a vector, it means whatever the size of this z, number of rows and column, it will be same. This a1 is also having the same thing. Got it? Yes. Now the next thing is, then once we have these a1 we have computed, what the network will do in the forward pass? Okay, what it is doing is that it is taking these weight matrix, multiplied it with this input, then added these biases, then whatever these, immediately it got all these z's, and then it passes all these z's through these activation functions, and it got all these a's of layer 1. And once it has these a's of layer 1, then it is ready to compute the a's of layer 2. Same thing it will do. Now it will compute the intermediate result z for layer 2. And that is nothing but weight matrix of now layer 2 multiplied by the activation of layer 1, which is nothing but this one, like whatever the network has computed these values as. Okay, and then add with it the biases of layer 2. Okay, and then from there you compute a2. What is the activation? Final layer activation is nothing but pass it through some activation function z2. You pass this z2 through some activation function, you will get the final layer output. Okay, now you see here, okay, although I wrote here like activation and activation, so I would like to distinguish here something, that this is the activation of layer 1. So I would like to write it here, the pass it through activation of layer 1 and then pass it through activation of layer 2. My point here is that these, don't you think that is a square I wrote, huh? Like it's not a square, it's just activation of layer 2. You see, my point is, why did I like distinguish this activation? Because the same activation function might not work on, I mean, you might not apply the same activation function on all the layers. But one thing is that I didn't write like activation 0 of layer, I didn't write like activation 0 of layer 1, activation 1 of layer 1. I mean, for all the neurons in that particular layer, we'll be applying the same activation function. Okay, but for different layers, you can apply different activation functions. And usually we'll see, specifically for the output layer, we usually, like use some specific or, like problem specific activation layers. Okay, sometimes we use linear even, like you will see when we do regression, then usually typically the activation function of the last layer is nothing but it's a linear activation function. So it doesn't do any non-linear computation on its input. Okay, but okay, I just wanted to make that point clear, that layer wise the activation functions could be different, but in the same layer for all the neurons, the activation functions are usually kept same. I mean, what exactly is the reason? I have not actually gone into the details of all these things. Maybe it is for simple calculation, maybe for easiness of calculation, and most probably the initial researcher, they didn't find much it useful, I guess, like using different activation functions for different neurons there. You know, I thought, like, you know, this approach was chosen by the rule of, yeah, you know, evolution, I guess. I mean, that was the simplest rule you could have, you know, like think of, and then it worked well. So, you know, that's the point. But the point, the main point, you do not forget that most of the times you'll see, like, okay, layer wise the activations could be different, but in the same layer activation functions are usually the same. Okay, done. Now see, the forward pass can be now written like this. I mean, only these four equations then. And these are matrix multiplication operations, and you can compute it like anything. I mean, in NumPy, using NumPy in Python, this is just like, it is only one line statement. That's all, right? So forward pass, it turned out to be very easy when you know, like this is the math for forward pass in an artificial neural network. Now our next task is, what is the math for the backward pass? Is it as straightforward as this forward pass? It's not there, because backward pass not only, you know, like it involves doing the computation as it is, but at the same time it involves this propagation of the error back from the end to the beginning of the network through this backprop algorithm, and then gradient descent is also involved there. So things are there, so we have to do some more like, you know, derivation to get to the final equations for the backward pass. Okay, now it's time for the backward pass then. Okay, so let's see what this network is doing, or what it is that we want the network to do. Okay, now you see this network here, like this network is taking two inputs. I mean, it is taking an input which have which is two-dimensional. Now you see here, rather than calling it as two input, you can think it of like, okay, now the input to the network is a vector, two-dimensional vector, and the output of the network is again a two-dimensional vector. Okay, so if you want to think concrete, now what you can do is, okay, you can think it of like this, the one probable thing that this network might be doing. But again, I'm saying it is just one probable thing. These neural networks, as you know, they are general computational model. It means that they can basically, you know, they can approximate more or less every function or any functions there or any operations there. But then also, for simplicity, just to carry out the examples, so that you can think, what you can think of is that, okay, at least from this diagram it is clear that it is, these inputs are two-dimensional, outputs are two-dimensionals. Now you just think of a problem then, like say for example, you have like you want to train the network for a reflection. That is, you give the network a two-dimensional point. This is your x, and this is your, this is x coordinate, this is x axis, y axis. Suppose if you give the network like say 0 1 2 3, this is just, let me like label them so that I can get some idea here. Okay, now this is 1 2, and so suppose the value of the input that you give is like 2 comma 1. So this point, in that case, what you want your network to produce is -2 1. That is, you want to produce the reflection with respect to the y-axis, and that's what you want to train the network for. So any two-dimensional point if you give, so like say for example 2 and then suppose 3 here, so the corresponding point will be this, the output should be this. If you give this point here, then the output should be somewhere here. So that's what suppose you want to train the network for. That is, you give the network this pair of input, like you give the network like, what is this, px and py, the x and y coordinate. This is your activations, I mean this is your a0 basically. Okay, this is your input, which is a two-dimensional vector. The first component is the x-axis of this point. Suppose you consider this is your point p. Okay, this is the x-axis of point, I mean x component of point p, y component of point p. Then we want activation 2 finally to be this you know, qx comma qy, where this is suppose q, x coordinate and y coordinate. That's what suppose we want the network to train for. Now this is just an example, like you can think of like what this network is doing. Okay, now you see here, when we want, the first thing is that initially we start with some random weights and biases. It means these weights are, these W1, these are some random numbers, B1 some random numbers, W2 random numbers, B2 there are some random numbers. So obviously then when you process these inputs, suppose I give now, initially these all these weights and biases are random, and I give this input like say for example here I give the point. So just assume that this point is say 1 2 3 4 4 comma say 2. This point is 4 comma 2, and the output that we want is minus 4 comma 2. X is minus 4, y will remain same, minus 4 comma 2. Now in that case, suppose now this input I give 4 comma 2 I give as input, and with these random weights and biases the network will try to compute the output. Then that output is certainly, it's a very less probability that that output will be minus 4 comma 2. That output will not be minus 4 comma 2. The output generated by with these random weights and biases could be anywhere. That point it can say, okay, that is this is the reflection of the point. This is Q actually. In the first go it might generate Q like this, but the thing is we know that that Q is not same as the Q that we want, right? So there is an error there. Like this is the error of the network for that particular input there. For this input it has generated, like instead of generating this as the output, it has generated this as the output. Okay, so and that error is happening because of these wrong weights and biases. The operations basically it will perform the same operations, only thing is that these wrong weights and biases. If these weights and biases we can set properly, then what we can achieve is that no matter what point we give, it will give me exactly the reflection point there. So there exists a set of weights and biases so that for any point the network can map that point to its by doing the same operation, it can map that point to this the reflection to its reflection point with respect to y-axis. That's possible. So from here what we know is that these now when we say we want to train the network, what we want actually the network to do is we want the network to actually adjust these weights and these biases. These are the parameters for which we want the network to train for. I mean, when we say the network is, we are training a network, basically we are figuring out what are these unknown weight matrix and bias vector, weight matrix and bias vector. Okay, so that's what we want our network to figure out, and that network will do that thing iteratively, like by doing a lots of forward combination. What the network will try to do intuitively, what the network will try to do is that, okay, it will try to take an input. See here, we need to have something called as your training data, where we know like what is the right value for this P. Each pair we will have something like this. We will have some known pair of P's and Q's. Okay, so this is known as our training data. So what we'll do basically is that we'll train this network. When we say we train the network, means we give the network a single point here. You can think it that way. We can give the network a single point, ask the network, now you compute me the reflection point. It will generate some reflection point, the way it has done for this P, suppose this Q. And then we know like that that is not right, because we also have that for this P we have Q, right? I mean, this Q we already know. I mean, we have that record, so certainly we can compute compare this generated Q with the actual Q, and then we can tell the network that, okay, you perform good or you perform bad. And not only this binary good bad thing, at the same time we can give the network a quantitative feedback, sort of like, okay, this much good or this much bad you are, or you can say like, okay, you are from the actual output this much away. Okay, we can tell directly, okay, a number we can tell the network, okay, you are from your desired output, you are 5 unit away, or you are 10 unit away. Okay, that number can tell the network, okay, how far it is from its desired output. Okay, and that farness, that quantitative measure of the error, like how far it is from, see here, this distance, you can think it of like it is the error. This distance from this generated output to the actual output, you can think it of like that is the error of the network for this specific input P. right? And when the network is properly trained, and when we say the network has learned, it means what? This distance will be, or this error will be minimum. And at best, what the best thing that we can achieve is, we can achieve like this q is exactly same as this q. It means the network has generated exactly the same point there, and at the time the error or the distance of this q from this q will be 0. You got the point? So from all these, whatever it is as I said, is that we need to now bring the concept of the, the cost function. Now a cost function is what? It is a function that you can use. It is a function that you can use to give the network a quantitative measure of the error made by the network. Now what I mean by this is, okay, now see here, there are different cost functions that you can use. The way you can have different activation functions, the same way you can have different cost functions also. But one very commonly used cost function, an intuitive cost function that you can think of, is this distance measure, right? I mean, you can think of, even if it is a three-dimensional point, you can think of like one three-dimensional point. You can think of like how far one three-dimensional point is from another three-dimensional point in terms of this Euclidean distance, right? So more or less the same expression you can use now as a cost function also. So basically the general need for the cost function is, or why we need that cost function is, we want that cost function to tell the network how good or bad the output is, and based on that quantitative measure, the network can actually update its weights and biases. That I'll come into a moment. But first, let's decide like what should be the cost function, or what you can use as a cost function. So one very commonly used cost function is, which I'll be using it here. This is very intuitive, that's why I'm using it, and it is commonly used more specifically when you are doing like say regression task, where you want your output to be like real number, continuous. Then it is very preferable actually. And even you can do classification also with this specific cost function. However, for classification task, you have better cost functions, okay? But to understand the thing, I think it's a very good candidate, and that good candidate name is mean squared error, okay? Now mean squared error, and what is the the form of writing means, or how do you compute mean squared error? You see here, this network will generate some output, right? And the output of the network, will say the output of the network is nothing but it is the output of the last layer of the network, right? I mean, whatever it is, the activation of the last layer, that only we can consider as the output of the network. So although they are the same thing, let me write here now this as the output 0 and output 1. It means we have this output vector. It has now, at least for this specific network, we have two components. This is output 0 component, output 1 component, and for this network, output 0 is same as activation 2 0, and output 1 is same as activation 2 of 1. Okay, I'm just giving a different name, like to say that, okay, that is the output that we're talking about. And the output of the network is usually always the activations of the last layer. Got it? Okay, now what we want is this mean squared error. What this mean squared error is, whatever it is the you can think it of like it is the mean squared error, you can write as is equal to, it is the sum of OI minus, it is the sum of OI minus OI minus YI whole squared, where I goes from 0 to say k. It means, what I mean by k is that, see here, our in this specific example, like suppose you just consider, okay, you consider that you want to perform that reflection operation, okay? So in that case, your training example will be of 2 dimensions, isn't it? It will have some x coordinate, it will have some x coordinate, some y coordinate. It will also the result will also have some x coordinate and some y coordinate. It will have, suppose x1 y1, then here also it is x1 say prime, y1 prime say, or whatever the way you want to tell it. But thing is that it will have two components there, right? I mean, each y, for these x, for if this is your x training x, then this will be your training y. Okay, now that's what this y I'm saying. Now what is this I then? It is this I, or this, you can say like k is the output dimension. You can say k is the output dimension. Okay, it means here in this specific example output dimension is 2, so k will be 2. I mean, here since I started from 0, so k will be 2, but I can write it like k minus 1. Okay, so more specifically, like if you want to write the cost of cost function for this network, you will write it in this way. In a compact way, it will look something like this. Specifically for this network, it will look like O0, the zeroth component of the generated output. From there, you subtract the zeroth component of the desired output, take the square, plus then you take the first component of the generated output. From there you subtract the first component of the desired output, and then you take the square. So whatever it is, this term, that is the mean squared error, and that we call as the cost of the network for this for one training example. Now see here, when you train a network, you can like train a network for every single example. Like you give this example, you say, okay, that is the error, then propagate the error back to the like first layer, and then you take the next example, then do the same thing, and then take the next example, then do the same thing. That is the like theoretically that is something that should happen. Okay, but to speed up the thing, what we do is instead of processing one input at a time, you usually process like a bunch of inputs there, and then we compute the cost for all those. Like suppose we are in it at a time, we are processing say 10 inputs. So in the time we'll have like 10 different cost values, certainly for each input one cost, 10 different cost values. So in that case we'll be taking the average of all those 10 costs. But for the time being, you don't need to worry. We can like think that we're not processing 10 inputs or something. We are not processing the inputs in batches. We're processing the inputs like one at a time. So things are very much simple. That one input, one cost, process the back propagate that cost back to the to the first layer. I mean, in this process you'll be actually updating the weights and biases. But why the cost should be back propagated? I mean, why this cost function is useful? First thing is that it gives us, certainly it gives us a way, like how far. It is a quantitative way of telling, like we know, like okay, if you tell me a big number, then we can intuitively think of like, okay, the output generated is far away from the output that we want it to generate. That is okay, fine. Now, then there is another significance of this cost function, and that is the most important one. And what is that? Is that this quantitative measure, whatever the cost function is saying, you see here one nature of the cost function. The cost function will be the value of the cost function. Say for example here, okay, suppose our y that we wanted to generate for some input, the y that we wanted our network to generate is, say for example, -4, and say this is -4 and y was, say for example, 0. That is what we want our network to generate for some specific example. But the network has generated, say, O as say like some number which is not -4, something like, say for example, 9, and it is not 0, something other than that, say for example -2. It has generated this, right? So in this case, if you compute this cost, then whatever the cost will be, one thing is sure, that the cost will be positive, and the cost will remain positive for all these different outputs possible, and it will become 0 only when the cost will become 0 only when your generated output, that is this component of the output, is exactly -4, this component of the output is exactly 0, then the cost function will generate the the cost of that training example will become 0, because it is same. If the zeroth component is same, then it is the 0. Then what first component is same, it is 0. Then 0 plus 0 is 0. So you will know, like, and that is the minimum thing possible. Other than that, any deviation from the from the desired output, it will always produce a positive cost. Okay. So now once we have that point, then immediately we can think like the network, that what we want now the network to do is that, for suppose for given no, for a given point, suppose for which this is the output, then instead of saying that for that given point generate this output, rather than saying that, what we can say is that, okay, for that given point, once the output is generated, and if we compute the cost, then we should get the cost as 0, and if it is 0, then we say that the network has learned the thing. It means what we are basically are interested in, that when we train the network, you can think it of like training the network, is like, we'll say the network is trained properly if the cost for each and every training example there is 0, or at least, you know, equal, almost equal to 0. That is, we want to minimize the cost for each and every training example there. Are you getting my point? What am I saying you? And that is what this neural network is doing. See, basically the neural network is performing an optimization operation. It wants to optimize the cost function. Whatever it is the cost function that you have selected, it wants to optimize the cost function. It wants to find the minimum value of the cost function with respect to what then? You want to find the minimum of a function. As soon as I said that, it is with respect to something. And with respect to what? With respect to the parameters of the function. So what are the parameters of this function then? I mean, you know, of this function represented by this network then. And the function represented by the parameters of the function represented by this network is nothing but all these weights and biases. Okay, so what we want now is, see, as soon as we have defined the cost function, this is known as the mean squared error cost function, like that. And now once that cost function is there, and once we see this specific thing about the cost function, and what is that specific thing is that the value of the cost function is equal to 0 only when the generated output is same as the desired output. And other than that, no matter what, it is always positive, right? It is always bigger than 0. So ultimately, and since we want, for all the training examples, we want the network to generate the right output, it means we want the overall cost of the network to be 0. It means we want to minimize the cost function. So ultimately, we can think of like, as soon as this cost is coming, or this cost function is coming, then we can say like, we want, then what we want the network to perform is, or what we want in our training phase is like, minimize the cost function, minimize cost function, or minimize this cost function. Okay, and this cost function C, now this cost function C, this is a function of what? Since I'm saying the cost function, it seems like cost function is a function of O and cost function is a function of Y. Now it seems like that, right? Now where, you know, this is square. In general, I'm writing the different terms that are sum of like OI minus yi whole square. It seems like the cost function is a function of O and Y. But you see here, for one training example, this Y is constant. Y is constant. So cost function is actually a function of O then, right? Now it means you can write cost function is a function of O. Cost function is if cost function is a function of of O. But the thing is, what is this O? This O is the generated output of the network. This O is the generated output of the network. And that generated output depends on what? It depends on all these weights and biases, right? So it means you can think like the cost function is a function of O. Apparently it seems like that, but ultimately what is this cost function is? It is a function of, this cost function is a function of all weights and biases of the network. It means cost function, you can think it of like, it is a function of like, say, W00 of layer 1, then W01 of layer 1, then W10 of layer 1, and W11 of layer 1, like that, and it is the last one. Say I started from here, and then it is like, say, W112, W1, I mean W2 of 1 2. Okay, not only that, and all the biases are also there, like bias 0 of layer 1 ... bias one of layer 2. It is a function. This cost function is a function of all these different parameters then. Okay, and what we want to do is we want to minimize the cost function. We want to minimize this cost function, isn't it? We want to minimize this cost function, which is a function of all these different parameters. And as soon as I say, like, I give you a function, you have to, I give you a function, and also I tell you, okay, these are the parameters on which the function depends. Then you have to minimize the, the function, and you want to find the minimum of the function. Then what you do is you can use gradient descent, and gradient descent says that, okay, if you now, what gradient descent says is that, like, if you update these different parameters, just consider one parameter, like, let's say, these are different parameters. Okay, let's in general represent them as parameter I. Okay, now you want to what gradient descent says that if you update the parameter pi, don't worry, it is this term that I'm using right now, pi, is very temporary. It will vanish in a moment. Okay, it's just for this step only I'm using this term. So these parameters, suppose you consider any parameter pi in general, it can be w00 also, w01 also, this term also, this term also, this term also. So in general, say, let's say that's pi. So if you want to update pi, and you want to minimize the function, then gradient descent algorithm tells you that you can go to the minimum, you can reach the, you can expect to reach the minimum of the function if you update each and every parameters of the function by this rule. And what is that rule? That the new value of the parameter will be this old value of the, from the old value of the parameter, then you subtract this thing, the slope of the function, the slope of the cost function with respect to that particular parameter. First you have to compute the slope of this function with respect to this parameter, and then you have to multiply that by a constant. Let me write here the constant as eta, and whatever that product is, that much you will subtract from the previous value of that parameter. Okay, and if you do that, you can expect that you are moving closer to the final solution. So why this subtraction you see here? It is actually this thing is saying that, according to gradient descent, it is saying that you are actually moving opposite to the direction of the slope, moving opposite to the slope of the function in that particular direction, or represented by that particular parameter. So you can think like this function is a multidimensional function, and then each parameter is a specific dimension, and in that dimension you want to take a step. Now which direction you will go, you will first compute in that direction what is the slope, and whatever it is the slope, you will go to the opposite direction of the slope. Okay, so it means you are like climbing downhill. Okay, you are at the top of the hill and you want to go to the valley. Then what you do is you go against the slope. If the slope is like upward, then you move downward there. Okay, so that's what it means, moving opposite to the slope, and that is opposite thing is coming, we are representing by this minus symbol. You see here, if this term, if the slope is positive, you are increasing, you are decreasing the value of the parameter, but if this slope is negative, then you are increasing the value of the parameter. It doesn't mean that when you are doing subtraction, it is always you are reducing it, no? Because it depends on this slope. If the slope is negative, then you have to increase the value of the parameter. If the slope is positive, you are actually decreasing the value of the parameter. Okay, that's what we say, like moving in the opposite direction of the slope. And what about this eta? Now, this eta is a constant. Eta is a constant. And that constant in terms of deep learning neural network, we call it as the learning rate, and that is a hyperparameter in the sense that that is a parameter that the network doesn't learn by itself. You have to, as a programmer or as a user, you have to specify that parameter to the network. Okay, so this is some input you give to the network, like you can fix this number to anything, like say for example 0.01 or maybe 0.1, and for some for some work, you can write even like 1 or maybe 2 like that, but usually they are kept very small. Again, I'm saying this is a hyperparameter, although I said anything, but anything is obviously not possible. You have to like keep your value within a certain range, and that thing you decide by mostly heuristically, okay, or by following your intuition from your previous experience and all. But if you don't know anything about it, say for example you have no idea how to set this value, one good way is that, okay, you set it to a lower value, 0.01 or something like that, okay, and it will work. And okay, that's the thing that I want to tell you right now about this cost function, okay. Sorry, about this learning rate. And once we implement the neural network, then we can like talk more about it. We can see that by varying this learning rate, what happens to the network. So those things we can discuss once we have our code ready, once we're seeing the output, then we can like change it, and we can we can try to get some more insight about that particular parameter. So for the time being, you can consider it as a constant, okay. That's just a constant like 0.01 or something. Clear? Okay, done. So this is the rule which is coming from gradient descent. And you see here, I'm saying that pi in general, but that pi could be replaced by anything. It means for all these different parameters, for all these weights and biases in the network, you have to first compute what? This is the crucial part, isn't it? I mean, you have to compute the partial derivative, or you have to compute the rate of change of this cost function with respect to that particular parameter. Once you have that thing ready, this operation is straightforward. Old value minus eta into whatever that derivative is. But main question computationally, I mean the math is this part here. How do you compute the cost of the function with respect to any parameter? When I say that, you see here, you see this neural network now. Okay, let me bring this neural network down, and then I'll be able to explain you. Okay, now see this neural network, say, so you give some input to the network, based on its weights and biases will compute this intermediate result, this output and all. So it will get some point here. Now from this O, you also have this Y, you also have this Y0 component and Y1 component. From this Y0 component and Y1 component, what you do is you compute the cost. I mean, from this Y0 and from this Y vector and this O vector together, you compute the cost, right? You compute the cost. Now this gradient descent is saying that like you have to first compute the rate of change of the cost function with respect to all the parameter. It means you have to, once this cost is like computed, what you want is you want to compute the rate of change, how much this cost, what is this talking about when I say rate of change of the cost function with respect to a parameter. Just consider the parameter, say for example this one, W001, okay, W001. Basically you have to do it for all, huh? This I just randomly chosen. So what does this mean is that you want to compute how much this cost will change if you do a small change here. Okay, that's a like question, isn't it? I mean, if I do a change here, like that will change this output G here, that will change again this activation value, that might again, once that activation value is changed, that since that output is now going to both these neurons, it might change the output of this neuron also, so it might change this part also, and that way it will do some change in the cost. But what exactly will be the change? I mean, if I do a small change here, I want to know how much the cost will change. But the thing is, this W0 is 001. I mean, this particular thing is not directly influencing the cost. It is not a direct equation from which you can compute. Okay, this much, if I do a change here, I will know that will have this much change in the cost. Rather, what we can see is that this W00 is linked with this cost function through some intermediate links or intermediate functions like W00, it affects Z0 affects A0 effects, both of these A0, two of A0 means both this one and that one, and both of them affects this cost function. So these effects are there. I mean, we need a systematic way of computing then, like a small change here, we want to compute how much, a small change here, how much it will change this cost function. That's what this term is saying. It is the rate of change of the cost function. How do you interpret it? You interpret it in this way, the rate of change of the cost function with respect to the the weight, a small change in W01, how much change it will do in cost function, or rate of change of the cost function with respect to the weight W001. I mean, whatever that term is. Correct? That's what we want to compute. And not only for this one, I mean, basically what we have to do is we have to do it for all these weights and biases. Basically, we have to compute the rate of change of the cost function with respect to W00 of layer 1. Then what is this we have to compute? Then we have to compute rate of change of the cost function with respect to W01 of the layer 1, and all. Basically, how much this cost function changes with respect to this one, 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 this B0, B1, B2, this, this one, like that. Too many things, right? Yes. And we'll see, like, although it, like, too many of them are there, but at the end there is an elegant way of doing the thing that boils down only some 2, 3, 4 operations like we had in our forward pass. Okay, but then also let's now see one thing. Intuitively, you just try to think how many such rate of change you have to compute. Right? It will be same as, see, ultimately what we want to do, we want to compute these rate of change for each of the parameter, and then we want to update each of the parameter. So these parameters are already there in this matrix format, right? So we have W1 matrix that represents all these weights. We have B1 vector that represents all these biases. Similarly, W2 we have B2 we have. So it means somehow you can think it of like, ultimately you have to compute what is the rate of change of the cost function with respect to with respect to all these different weights there. So what you can think of is that ultimately what we want to compute is, we want to compute another vector, say, let me call it, say, DW. This is another matrix DW1 that will encode all the rate of changes. Now what is this? How many terms are there? 3 rows, 2 columns, right? So here also it will have 3 rows, 2 columns, but this will be the rate of change of the cost function with respect to W. What did I write here? 1, no? So let me write it 1. This is 1. Okay, with respect to W100, then rate of change of the cost function with respect to weight 01, and similarly rate of change of the cost function with respect to 110, DW111, DW120, and DW21 of layer 1. So this is what we want to compute for this W1. I mean, see, this W1 and this W1 and this DW1, they will have the same size, right? I mean, same size. So directly you can write, like, if we know how to compute this, then at the end this operation will be straightforward. So what we want then at the end, we have to multiply this matrix by some constant eta, and then from this matrix we can subtract that this matrix, right? That work will be done. Only question left is now, how do you do that? And not only for W1, similarly for B1 also we'll have a counterpart. You see, for B1 we will have to compute what is DB1 then. What is DB1? And that will have how many components? It will have, like, what is the rate of change of the cost function with respect to the zeroth bias of layer 1? What is the rate of change of the cost function with respect to the first bias of layer 1? What is the rate of change of the cost function with respect to the second bias of layer 1? So this another vector we have. Similarly, we'll have a, for this one is corresponding, this one will be corresponding with this one, and similarly we'll have one for this weight matrix. We'll have one rate of change vector for this biases there, right? Got it? Okay. Now don't worry, we are like in a transit state now, like where we're still in the explosion phase. At some point of time you'll realize now it will again collapse everything to a single point there. Okay, now we are sort of like exploding right now, so don't worry, don't lose hope now. Okay, now you see, let's now concentrate. how do we compute these individual terms there, individual terms? Okay, let me, just for the sake of completeness, let me write the other terms also, what that we want to compute. We want to compute not only dw1, we want to compute dw or rate of change of the for all the components of weight matrix 2. It is like, see here, we have 3 rows and we have like 3 columns, 2 rows. It is like weight here, this thing, weight 0 0 0 1 0 2, that is the first row. 1 0 1 1 1 2, that is the second row. So weight 0 0, weight 0 0 0 1, weight 0 2, and w10, w11, w12, right? Those are the things, those are the things. And for each, that is the w matrix, right? But we don't, no, this w matrix is this one, but this dw2 is means it is the rate of change of this particular weight with respect to the cost function. I'm simply writing it as dw0. It means rate of change of this one with respect to the cost. And then same thing, this one is this, and then this, and then this, and then this. It's just a notation I'm using. I mean, dw02, it means this thing you can interpret as it is the rate of change of the cost function with respect to a small change in this. Okay, so similarly, if you want to interpret this, that is rate of change of the cost function with respect to a small change in w10. Clear? So same way, so for this matrix, this w2 matrix, this dw2 is the corresponding part by which you want to update, and the last one is this b2. So we'll have a component, like we'll have a vector db2, which will look like how many biases are there in the final layer. We want 2 neurons there, so 2 biases there. So bias is 0 of layer 2, bias 1 of layer 2, and it means we want to compute the rate of change of the cost function with respect to this bias and rate of change of the cost function with respect to this bias. That's what we want to compute. You see here, ultimately we want to compute this matrix there, this vector, this matrix, and this vector. These are the 4. Ultimately, out of all these different, like tens of different parameters, now we pack everything into 4 things. One is this matrix, another one is this vector, another matrix, another vector. For each of these weight matrix, we'll have a corresponding rate of change, corresponding, like slope matrix, or you can call it sometimes error matrix also. For each of these bias vector, we'll have the corresponding error vector. Similarly, like that. Got it? Okay. Now we know what to compute, but still the question is, how do we compute these matrices? I mean, is there a way? I mean, can we do it? To know that, first explode. Okay, explode in the sense like, now see what we will be doing is, let's first start with this. We want to compute the rate of change of the cost function, say, with respect to b0. How will you compute? Okay, so let's try to do that, like if we can do it, and let's try to first manually figure out what is the rate of change of this one with respect to this, what is the rate of change of this one with respect to this, what is the rate of change of all these 3 with respect to this, all these 3 with respect to this. Slowly and slowly we'll building the thing. Okay, it's going to be too long, I guess. I'll break it down into multiple parts. Okay, now let's consider this network, and here we, from these O's, and we have these Y, from these O's and Y0 and Y1, we know, like from these Y and from these O, what we do is we compute the cost. Okay, we compute the cost, and it is nothing but it is sum of OI minus YI whole square. As many i's are there. Okay. Now we are interested in computing the rate of change of the cost function with respect to b0 of layer 2. b0 of layer 2, right? So that thing, and so you can think of, like, if I do a small change here in b0, it will affect this o0 component, but it will not affect o1 component. But that o0 component, change in that o0 will certainly do some change in the cost function, because cost function is like, taking the sum of from both this part, right? You can see that, right? So if I do a small change here, certainly it will do a small change in the cost function, and a small change, that small change will propagate to the cost function through this line, I mean through this part. It will not do any change here. Okay, so that way you can compute the cost function, rate of change of the cost function with respect to b0. That way, this thing, instead of trying to compute it in a single go, you can do it in this way, right? First you compute how much this link-wise from the back, from the last part. That's why it is sort of back propagation. I mean, you do it from the back till the front. Rate of change of the cost, and okay, rate of change of the cost, here you want to compute the rate of change of the cost with respect to this, with respect to a small change in this output 0, and see this output 0 and activation 0 of layer 2, they are the same thing. I mean, rate of change of this thing with respect to this thing is 1. Or you can say like they're the same thing. Okay, so you can say like rate of change of now, and then how much this output is changing with respect to this z0. You can compute rate of change of output 0 with respect to z0 of layer 2, this thing, and then you can compute like this, how much this z changes with respect to a small change in this b02. So how much this z changes, that z0 changes with respect to a small change in this b02, Okay, now the expansion, that is the way I expanded this term to this term, this is known as the chain rule of partial derivation, partial differentiation. Okay, chain rule, basically this is known as the chain rule. So what we are doing here is that we are like following the chain of events, and then we are trying to compute the then we're trying to compute the differentiation at each link, and then we are multiplying the differentiation at each link together to get the end-to-end differentiation, sort of, right? Rate of change with respect to the rate of change of this one with respect to the b0, we are actually computing all the links through which they are connected. The rate of this cost depends on O, so that's why rate of change of cost with respect to O, and then this O depends on Z, rate of change of O with respect to G, and then G depends on B, so rate of change of Z with respect to B. Okay, so that's what we're doing. And see here, each term is now, you can express, or you can write the equation for each of this term, because z0 depends on b0 directly, z0 depends on b0 directly, and o0 depends on z0 directly, o0 depends on z0 directly, and this cost depends on o0 directly, this cost depends on o0 term directly, isn't it? Yes, right? Right, okay. It means we got some, we are now one step closer. But then also, what is this? I mean, what is the rate of change of the cost function with respect to the output 0? What is the rate of change of the cost output 0 with respect to this and this? What is this? We have to figure it out, okay? So let's try to do this now. What is the rate of change of the cost function with respect to output 0? What is that? Now let's see. What is the formula for cost function? Just expand it, you will get the answer. So the cost function formula is like this: output 0 minus y0. I'm just doing it for this specific network, but whatever I am saying, it is quite general, and you will try to appreciate, you'll be able to appreciate it in a moment. But for this simple example, what is cost is cost, I have written it in this way, or here somewhere I wrote the cost as the expanded way. Yeah, here o0 minus y0 whole square, o1 minus y1 whole square, right? That is your cost, right? For this simple example, you can write o0 minus y0 whole square plus o1 minus y1 whole square. We want to compute the rate of change of this function with respect to d of o0. Okay, great. Then what is this then? Don't need to worry about it. You see, o0 term is only in this, in this part o0 is there. I mean, only this component is dependent on o0. This is not. So if you do a change in o0, this thing is anyhow not going to change. So rate of change of this part with respect to o0 is 0. right? So ultimately the question is, what is the rate of change of O0 minus Y0 whole square divided by a small change in O0? Now what is this actually? What is this? What is this? It is same as you are asking, it is like, what is the rate of change of, okay, since it is same, let me write it here. What is the rate of change of some variable x minus some constant 5? You see, y0 is a constant. The output is constant there. That is what we want. So x minus 5, rate of change of x minus 5 with respect to x. So if you know from our understanding of basic calculus, we know that like rate of change of x minus 5 whole squared by with respect to x is nothing but it is twice x minus 5. Okay, so same way here also, O0 minus Y0 whole squared with respect to O0 is then directly we can write now, right? Is then twice O0 minus Y0. Okay, now again, for mathematical convenience, we can think it of like it is only O0 minus Y0, whatever the zeroth component. And you might be thinking, why the 2 gone? See, easily we could have said that the cost function is sum of all these divided by 2. You can assume that there is a half. You can multiply the cost function by half. It doesn't change anything about the nature of the cost function. Okay, and if that half is there, then in this partial derivative also there will be this half in front of it, half in front of it, and that half will come here also, and that half gets cancelled, then you'll get it. So this is just a mathematical like simplification so that we can do the math easily. Okay, so don't worry, math allows us to ignore these two right now. Math allows us to ignore these two. Okay, but if you want to convince yourself, you just assume that the cost function is not actually the sum of all these terms. Then whatever the sum we get, we divide it by 2. Okay, and then you take the differentiation, that 2 and half gets cancelled, then you get ultimately this. Okay, so we got it. Now see, rate of change of the cost function with respect to output 0 is output 0 minus y0. If I ask you again, okay, that is done. Say for this particular term, we have computed now O0 minus Y0. What is the rate of change of the output with respect to DZ0? I mean, now the question is then this: what is the rate of change of the rate of change of output 0 with respect to DZ0? What is that? What is that? Let's see. What is this output changing? How this output is changing if we do a small change in, I said no, this output and this activation, they're the same thing. So it is same as asking like how much this, it is same as asking this question: what is the rate of change of A0 of layer 2 with respect to DZ0? Okay, got it. Or you can apply the rule of chain rule also, like how much this changes with respect to this and how much this changes with respect to this. Since O0 changes with respect to A0 as 1, so basically rate of change of O0 with respect to Z0 is same as rate of change of A20 with respect to Z0. Understood? Okay, so basically these two terms are same, but then also it doesn't simplify. I'm just writing, instead of writing O0, I'm writing A0 here. But does it simplify the matter? No, we still have to know what is the rate of change of this value here with respect to the cost function. And see, it depends on the activation function. Now that you should realize that rate of change of this A0 with respect to Z0 is nothing but it is the derivative of the activation function I'm using here. Okay, as I said, no, this is your I have written, no, here it is activation 2 function. It's a different activation function. It could be a different activation function from these layers, this activation function. So let me write it like this two way. I mean, this is activation function 1 and this is activation function 2. Okay, so they can be same, they can be different, but we want to make it like, say, okay, this is one, this is another one. They could be same, but they could be different also. So activation 2. So now this thing, rate of change of A0 with respect to Z0 is nothing but it is the derivative of activation 2 function, activation 2 of whatever that input it takes, Z. So for a time being, instead of like, and see what derivative of the activation function will depend on what activation function you are actually using, right? So so instead of like going to the specific form, as I said, now in the forward pass also we didn't do that. We didn't like fixed ourselves with some fixed activation function. We just said that okay, that thing is this activation 1 and activation 2. You see, I wrote it as activation 2 function, but what exactly is the form of the function? That depends on your implementation, what function you want to take. But the thing is that whatever it is, this function you are taking, in this case here you have to take the derivative of the same function. So let me write it in this way. This activation 2 prime of z0 of layer 2. That's how we are writing, where activation 2 prime represents the derivative of activation 2 function. Okay, and if it is a ReLU, it will have different value, and if it is a sigmoid function, then it will have a different value. Don't worry, in our final equation it will appear as activation 2 prime and activation prime only, but when we implement it, then we can replace this thing as by its original form. And see, these are just the derivative of some specific function there. You know the function, you know the derivative of the function. Both these two things are known, so you don't need to worry about it. Okay, got it? So just proceed with me, things will make sense, huh? Don't worry. So we have computed now all the there is one more term left, right? So we know how to, what is this rate of change of the cost with respect to output 0, which turned out to be this much. And then we know at least how to write this value here. So it turned out to be the activation 2 prime, which is nothing but the derivative of the activation function, and with respect to that z02. Okay, things will this is basically what it is saying, that it is this thing is what it is, the rate of change of the activation function with respect to z02. I mean, this is z02, no? z02, you see here, that is z02. Okay, so z02. So here z02, then rate of change of this activation prime means what? Rate of change of the activation 2 function. Rate of change of the activation 2 function when you give the input as z02, how much the value of this function changes if I do a small change in z0. That's what this activation 2, I mean this particular term represents. Okay, and you see here, whatever the activation functions we use such functions whose derivative we already know. Okay, so when you try to implement it, activation, I mean implementing this thing is quite straightforward, and I'll show you this thing when we actually implement this neural network. But before that, for simplicity, I'm just writing this term as activation 2 prime of z02. You should understand that what actually it means. It means this rate of change of the activation function when you give the input as z02 with respect to z02. Okay, or you can say like how much the output of this function changes if I do a small change in the input of the function. Okay, so we now know all the 3 terms. You see here, well, no, not all the 3 terms. We still have this left, z0 by b02. Now we want to compute what is the rate of change of the z02, how much this term changes with respect to a small change in b02. Okay, and what is that? For that, we have to now replace this z02 by its its z02 is a value which is computed by which was computed by performing some mathematical operations, right? I mean, what is z02? If you see here, what is z02? It is the weighted sum of all these inputs there, right? It is a01 multiplied by 002, then this one into this, plus this one into this, plus b02. That was z0. So let me write it. It is like z02 is nothing but it is the weight of layer 2 zeroth neuron coming from 0 neuron multiplied by the 0th neuron of the previous layer, plus weight 01 of layer 2, and then the activation of the previous layer neuron 1 of the previous layer, and then plus weight, see here, how many weights are there? There are 3 weights there, right? I mean, weight 02 is also there. So plus weight 02, I mean, weight of the 0th neuron coming from the second neuron of the previous layer, and this weight is of second layer, but here this is second neuron of the previous layer, means A1's 2 neuron. Okay, so that's all. And then plus we want to add here, or we add here the bias term B02. That is what this Z02 is. Z02 is the weighted sum of the inputs. See, there are 3 inputs there. There are 3 inputs, 0, 1, and 2. We take the weighted sum, multiplying them by these corresponding weights, and then we add this bias. And that's what Z02 is, isn't it? That's, I just expanded it here, okay? And we want to compute the rate of change of this particular term there with respect to DZ0 and 2. Now it is asking, like, if I do a small change here, how much this term will change, or how much this sum will change. Now see, in this sum, does it depend? If I do some change here, will it change this particular term? Will it change? It will not change, because there is no Z0. This term is nowhere, it doesn't depend on Z0 anyway, right? So it will not change. Oh, sorry, this is not Z0, huh? I just wrote it wrong. I'm sorry, extremely sorry for that. That's what I was thinking. How come this Z0 is coming in? Now we want to compute it with respect to B02. Okay, now let me ask you the same question now. Does this term changes with if I do a small change in B0? This term doesn't change. You just see. If I do this increase or decrease this B0, is it like going to change anything about this product A01 into W02? No. This product will always remain the same. You know, if I make it 100, 0, 500, this B0, anyhow, it cannot change anything about this product. Same way, it cannot change anything about this product. It cannot change anything about this product. So rate of change of this product with respect to B0 is 0. Rate of change of this product with respect to B0 is 0. This product with respect to B0 is 0. It means rate of change of this term is 0, this term is 0, this term is 0 with respect to B0. Only thing that changes, I mean, with respect to B0 is this B0 itself, right? Now, how much this B0 will change if I do a small change in B0? It will be proportional to 1. The amount you change in B0, the same amount you will change in B0 only, right? That's the same question. It is basically now, this boils, at, you know, like these are all zeros, right? So it is ultimately asking, what is the rate of change of B02 with respect to itself, B02? It is same as asking in the question, what is the rate of change of X with respect to X, which is 1. So this is also 1 in that case. Okay? So now we have computed all these 3 terms there. First is, like, now write it down. What is the rate of change of C with respect to O0? It turned out to be O0 minus O output 0 minus Y0. That's okay, fine. Multiplied by, what is the rate of change of output 0 with respect to Z0? So it is this activation 2 prime Z02. And it is like this. I'm just writing this. It is the derivative of the second activation function. That is the derivative of the activation function at layer 2. And you know, when the input to the activation function was this. That's all. And then this term multiplied by, what is the rate of change of Z0 with respect to B0? What is the rate of change of Z0 with respect to B0? It's 1. So it's simple, now 1. So this 1 you write, you don't write, it is the same thing. So ultimately this dc by db, it is like rate of change of the cost function with respect to B02 is nothing but it is O0 minus Y0, this term, multiplied by activation 2's derivative when the input is Z02. So okay, now although it looks but it looks pretty right now, right? I mean, if you don't worry much about this derivative of activation function, and I'm saying you, like, you don't need to worry about it. When you do it programmatically, it becomes very straightforward, just like calling a function there. Okay, so you're multiplying it by, you know, this term by this term. That's all. Now done. Now let's see what is okay. Now suppose this is done. Okay, now you see this thing, rate of change. Okay, Now once it is done, once we know how to compute this, then let's try to compute this then. Okay, what is the rate of change of the cost function? What is the rate of change of the cost function with respect to b1 of layer 2? b1 of layer 2, what is the rate of change of the cost function? How much this cost changes with respect to now this term? We are interested in, if I do a small change here, how much this cost will change. Again, we can apply the same chain rule here. Now I can write directly rate of change of the cost function now with respect to the output, the one output there, this component here. How much the cost function changes if I do a small change here, and or you can, that's how you can process. How much the cost function changes if I do a small change here, which is nothing but same as here, and then how much this thing will change when I do a small change here, and then how much this thing will change when I do a small change here. Okay, chain rule you can apply. So dc by do0, then how much this do1 changes with respect to dz1 of layer 2. Now see, this do1, this particular term depends on dz1 of layer 2. It doesn't depend on g0 of layer 2 or something. It depends on this one, and that dz1 and that dz1 of layer 2, that that depends directly on b1 of layer 2. Okay, now let's compute this then. What is the rate of change of the cost function with respect to O1? What is the rate of change of the cost function with respect to O1? Previously, we have computed what is the rate of change of the cost function with respect to O0, which turned out to be O0 minus Y0. So if you now generalize the thing, what will be the rate of change of the cost function with respect to O1? When it was O0, it was O0 minus Y0. Then when it is O1, you can directly think like it should be O1 minus Y1. That you can follow, that is now following your intuition. But mathematically, if you see, it is okay. You can see here now, what is the rate of change of the cost function with respect to O1 now? Okay, let me write it here. I mean, here itself I can write. Where do I write? Here. Okay, let's see. What is the rate of change of the cost function with respect to O1? And what is this cost function is? It is O0 minus O1 whole squared plus Okay, what is the rate of change of the cost function with respect to O1 is actually, it is, what is the cost function? It is O0 minus Y0 whole squared plus O1 minus Y1 whole squared, and then we want to assume a half in front of it for mathematical convenience. With respect to what is the rate of change of this function with respect to this one, it means if I do a small change in O1, how much this function will change. Now from our previous argument, it will be same as half of the rate of change of this O0 minus, rate of change of this O1 minus Y1 whole squared over the O1. Why this term is cancelled? Because this term by any means it doesn't depend on O0, O1, so it will be 0. Rate of change of this thing is 0. So ultimately this, and then again Y1 is a constant, so it is like X minus a constant whole squared with respect to X. So basically it is like half is there, and then it is twice X. X is this time O1 minus Y1. Half of get cancelled, so it is O1 minus Y1, and that's what we initially assumed, or generalized, right? O1 minus Y1. That's okay, fine. Now what is the rate of change of the cost function then with respect to, what is the rate of change of this O1 with respect to Z1? How much the O1 changes if I do a small change in Z1? That's the question, is this, how much this O1 or A1 changes if I do a small change in Z1? That is nothing but the the derivative of the activation 2 function itself. So but that time input will be, instead of Z0, it will be Z1. So it is the same derivative, activation 2, this is the derivative of activation 2 function, but the thing is when we give the input to the activation function as Z12, that's all. Okay, like the same, we are actually, this activation derivative of the function will be same, only thing is that based on this input the output will be different. And don't worry, again I'm saying like just take it as it is for the time being. Once you see the implementation, things will make perfect sense to you. Now only thing that we're doing is I'm going through the math Okay, and this math is important, and you might be thinking, am I going like I'm not sure whether I'll be like releasing it as the same video, or maybe I'm doing it in parts. I'm not very sure about it, but I think it's going too long, no? But there is no other way. You have to do it like, step by step if you really want to understand it. O1 minus Y1 into activation. This is activation 2 prime and Z1 this. And then what is the rate of change of this Z2 with respect to B1? Now, can we skip here something directly? I mean, see, if, how did we compute, what is the rate of change of Z0 with respect to B0? I mean, rate of change of, what is the rate of change of this Z0 to, I mean, how much this one changes with respect to this one is 1, no? Similarly, if I ask you the same question, how much Z1 changes with respect to B1 is 1. Because you see, Z1, the other terms are like this one into this one into this one, and this one into this one. So if I do a small change in B1, these products will remain same, so they will not change. So the rate of change of all these products will be 0. So if I do a small change in B1, the proportion, it will, this Z1 will also increase proportionally. If I increase B1, Z1 will also increase. If I decrease B1, Z1 will also decrease, because that B1 is linked to Z1 by a summation term, by a summation term here. Okay, so directly we know like that the rate of change of Z2 with respect to B12 is 1 there. But if you want to derive it, what you can do is you just expand the same thing you do, but only thing is that it is Z0, Z1 of layer 2, B1 of layer 2. This Z1 of layer 2, B1 of layer 2. Ultimately it will be 1. Okay, so it is done. Now that is your now the other part, other component is also calculated. This other component is also calculated. So we have computed this B0, what is the, how much we want to change here, how much we want to change here. Both these terms we got. So ultimately which factor we have computed, we have done this. We have done this db2. So we can write now what is this db2 as db2. We have computed db2 is equal to, it is this vector, but okay, let's see, it is equal to rate of change of the rate of change of the cost function with respect to db0, and rate of change of the cost function with respect to db1 of layer 2. This is what we have computed. Okay, and this is equal to nothing but this value here, O0 minus Y0 into activation 2 prime of Z0 2, and this is O0 O1 minus Y1, and then this is activation 2 prime when the input is Z1 of layer 2. Okay, so that this is this thing. Can we do better? Okay, now for simplicity, I mean, we'll be making use of it now in a moment in the future. So let's call this term, let's call this entire term, writing this entire time again and again, let's call this term as say, for example, I want to call it DE0, and I want to call it DE1. You might be thinking, so why? You could have called it db0 or db1 or something like that. Why did I call it like that? So this term I want to call de0 of layer 2, and this is de1 of layer 1, layer 2. I'm sorry, layer 2. Okay, it means it is the error at layer, this is the like error, this de2 0 represents the error, E stands for error at neuron 0 of layer 2, and this is the error of neuron 1 at layer 2. It means it says you the error at this point. Okay, error at this point. This is this term I'm writing here. This term is like this E0 of layer 2. Yes, right, that is the error at neuron 0, and here I'm writing this part is like the error at neuron 1 of layer 2. Why did I give it a name? You see that that error is actually when that error for b0, how much we want to change b0, rate of change of this cost function with respect to b0 is nothing but the error of the neuron at that term. You see, that term will again and again come. I mean, the same term will come when we want to compute the rate of change of all of them, like that. Okay, so what you can think it of is that, okay, before computing this db2, what we first compute, that we first compute this intermediate components. Okay, and whatever it is, that is this db2 is actually de2 is same as db2. So you sort of derivative, like how did we get this, but now I'm doing a slight twisting thing. Instead of computing like in the back propagation, first what we will do is in back propagation first, I'll summarize that thing at the end, but anyhow, it's just here I want to tell you something, that in the back propagation first we'll be computing what is this de vector of layer 2 is, what is this de2 is. First we'll compute what is de2, I mean de2, I mean the error at layer 2. Okay, so that thing is equal to, it's now see O0 minus Y0 into activation 2 prime of Z0, and this into this thing. So what you can think it of, like it is a these two terms, you just now separate them. It is O0 minus Y0, O1 minus Y1. So basically what it is the output vector. So this is a vector now, right? This is the vector. So output vector, this is your output vector minus the desired output vector O minus Y, O minus Y, O minus Y. Now it is just like vector minus vector. So if for the zeroth component you will get this term, for the first component you will get this term. Okay, multiplied by what? You're multiplying it by what? This activation prime of 2, that is the whatever the activation function you are using in the second layer, that prime of 2, and then in here you are passing, see, first z0 and z1, so you are passing this component, this z2, this vector you will pass. So activation 2 prime, it will act upon the way activation function acts. If you pass a vector to the activation function, what does this activation function do? It just acts on each of the component of the vector. Same thing here also, the derivative of that activation function, if you pass the vector, then it will work on each vector independently. So basically what you're doing is de2 you will be first computing, that is when you do back propagation, you will be first computing the output up to that point. The forward pass will tell you. Then you do back propagation. Then you start doing back propagation. So in back propagation, first thing that you will compute is, you will first compute what is the error at layer 2. What is the error at layer 2 means what is the error which propagates up to this point. Okay, up to this point. Okay, so that error is actually, see here, the error at this point multiplied by the the derivative of this, the error at this point multiplied by the derivative of this. So in general, when you write it like it is error at layer 2 means this error at this particular point, you see it is what we are computing is, we are computing O minus Y. Since you have O, you have computed, in the forward pass you have computed O, so you can easily compute now O minus what is your desired output. So the vector minus vector will give you another vector. So that vector, what you do is you multiply with the the activation, the differentiation of the differentiation of the derivative of this specific activation function, whatever it is that you are using, the correspond by the derivative of that activation function, you have to multiply this O minus Y. Okay, and the derivative of the activation function, you'll pass this vector. Got it? So this term you will be computing. de2 is a vector ultimately. That thing should be clear. Okay, done. Now we have seen, now once you compute this error, then what you will do is you can now write something like this. Now rate of change of the, now this is the error at layer 2, but this is the rate of change of the bias factor or rate of change of the biases of layer 2 will be same as whatever it is, or it will be proportional to the whatever it is the error at layer 2, whatever it is at the whatever it is the error at layer 2. Okay, so how did we know like db2 is same as de2? What is db2? First of all, db2 is the rate of change of the cost function with respect to zeroth component of zeroth bias and the first bias. This db2 is basically a vector. We want to know what is this. And what is this? It is de2, because we have already derived like rate of change of the cost function with respect to b02 is this much, which is nothing but the error, the zeroth component of this error vector, and rate of change of the cost function with respect to b1 is this much, which is nothing but the first component of this error vector. So basically these two vectors will be the same. Okay, so rate of change, or in general you can think like how much the error will change if you do a small change in b0. And see, this error is like, at this point that error is that error depends on this z0, which depends on this b0 linearly. So that e0 also depends on this b0 linearly. You got the point? That's the intuition behind it. Okay. Okay, now we have computed db2. That vector is done, computed. But to compute db2, we'll be computing this intermediate vector. Now we'll be doing some intermediate computation. So I'll be writing this intermediate computation as circles say. And this is what, or this is one thing that we actually want to compute for further processing, db2. And that's this. See, we initially decided, what are the things that we have to compute. So db2 we have computed. This is done. Now this is really done. How do you compute db2? It is just by using this formula. db2 is equal to de2, where don't you think this is a square? It is like error at layer 2. What is error at layer 2? It is nothing but whatever the output generated from there, subtract the desired output, multiply that thing by the derivative of the cost function. That just the function call basically, okay, with a vector. Whatever it is, it returns. You just multiply that thing with this vector, the like component wise multiplication, then you will get this de2. Whatever it is, that is db2. Done. We have done this thing. We have done like db2 part is done. Similarly, now we are going to now do dw2. Now we have done these biases of layer 2. Now we have to do weights of like how much these weights we want to change with respect to that is how much this cost function changes with respect to a small change in any of these weights. That's what we want to now compute. So it means let's start with the first one. See, so that I don't have to scroll again up and up a lots of time. So what I'll do is I'll just copy this image again. Okay, now what we want to compute is, let's say, what is the rate of change of the cost function with respect to, if I ask you dw2 0 that is we want to change find what is the rate of change of this cost function with respect to this particular term. Okay, so it is same as, now we'll be using the rule of like chain rule. Now by this time you are used to, so directly I can write rate of change of the cost function with respect to, now with respect to this w0. Now w0 changes only z0. It cannot change anything about z1. So this line you don't need to worry. So z0, that changes a0, that changes, or that is same as o0, that changes cost. So rate of change of the cost with respect to o0, then rate of change of o0 with respect to z0 of layer 2, and then rate of change of z0 of layer 2 with respect to what? With respect to a small change in weight 0 of layer 2. Weight 0, which is coming from the 0th neuron of the previous layer. Okay, done. Now what is this? Rate of change of the cost function with respect to O0, rate of change of the cost function with respect to, I mean, these two terms. You see these two terms? Rate of change of the cost with respect to O0, rate of change of O0 with respect to Z20. What is this term? That term is this term, right? I mean, these are the same two terms, right? Rate of change of cost O0 and rate of change of this thing is this, which is nothing but O0 minus Y0 into activation 2 prime of this, which is nothing but what? which is nothing but this term, no, this term, what I called it by this name DE0. Like see, O0 minus Y0 into activation 2 prime Z02. That is nothing but DC by DB02. DC by DB02 means this thing. No, and what is this thing is, it is multiplied by 1, you get cancelled, so ultimately this DC by DO0 multiplied by DO0 by that DZ0, that thing we said as, or we gave it a name as the error at the 0th neuron of layer 2. Okay, that's what this thing is. That's what this thing is. It is the error. This term is actually the error at layer, this is the error at layer at neuron 0 of layer 2. That's right. So another way of thinking it as, like, you see, you want to compute the rate of change of the cost with respect to W002. I mean, you want to compute the cost, rate of change of this cost with respect to this. Okay, so what it is actually, whatever it is, the error propagated up to this point. I mean, see, when you wanted to compute the rate of change of the cost with respect to B0, it was like whatever it was, this error up to this point, and then the relationship of Z0 with respect to B0. The same thing is true for this W1 also. Anyhow, that error has to propagate up to this point, and that will be the same. Like whenever if you were trying to compute the error for B0 or W00 or this one, the error at this point for all of them will be same. Only thing is that now that thing should be multiplied with the rate of change of this Z0 with respect to all these terms. If you're computing the rate of change of B0 with respect to cost, then what is that error you have to multiply with the rate of change of Z0 with respect to B0, which turned out to be 1. And that is why rate of change of B0 with respect to rate of change of the cost with respect to B0 is same as this error here. Okay, got it? Now the same thing, now we are trying to find out what is the rate of change of the cost function with respect to this term. It is up to this point the error is same, rate of change of this cost, and then Z0 is ultimately whatever it is, this term DE0, that we already have computed. What is DE0? DE0 is nothing but the 0th component of this particular array or this particular vector there. Okay, so DE0, then that thing should be multiplied by, now what is the rate of change of Z0 with respect to W00. Directly you can see that. I mean, how much this Z0 will change if you do a small change in this. If you do a small change in W00, that 0 will, the change in Z0 will be proportional to by whatever it is the term with, you know, this Z, that W00 is multiplied by with, and that is A01. So that is directly, it will be A01. Okay, rate of change of this Z02 with respect to W002, I'm writing it as A01. You might not be happy with that. You might want to see a derivation. So let me write it. Although I said it that way, but let's see why it is so. So what is that Z0, Z02? Let's write it now. Rate of change of Z02 is what? What is Z02? It is this term. It is the weighted sum of all these inputs plus this. So I already wrote it somewhere, but then also let me write it now instead of copying it there. It'll take me the same time. Rate of so it is like W002 multiplied by A01 plus W01 of 2 multiplied by A1 of 1 plus W02, this way, W02 of layer 2 multiplied by the corresponding input is A2 of layer 1 plus we have this bias term added there. So B0 of layer 2 with respect to this, we want to, I mean, rate change of this term with respect to W00 of layer 2. Now you see, if I do a small change here in this way, is it going to change this product? No, nothing will change about this product, nothing will change about this product, nothing will change about this B0. It means rate of change of this term is 0 with respect to W00. This term is also 0 with respect to W00. This term is also 0 with respect to W00. So what ultimately we are computing? We are computing what is the rate of change of W002 multiplied by A01 with respect to W002, and it is same as it is equivalent to asking this question: what is the rate of change of AX with respect to X? And it is A. So here A means A01, so that is A01. A01 means 0th neuron of the previous layer, first layer. That's what I wrote it here. And it is quite obvious here. How much that Z function will change, Z value will change if I do a small change here. And it will be proportional to by which it is multiplied by with. That is A0. So it is this. So if I now ask you the same question, what is the rate of change of Z0 with respect to Z012? Without doing all these steps, you will be saying me, okay, that is nothing but A1, because that's what, because if I do a small change, here, only this product will change, this product will not change. So rate of change of this product will be 0, this product will be 0, this bias will be 0, only this product will change. And what is the at what proportion that product will change? That product will change by whatever this constant is. If it is big, then it will change big amount. If it is small, it will change small amount, right? So it will be proportional to it is A1. Are you getting what I'm trying to say you? Just thinking ahead, sort of. Okay, now done. Now that is done. Now we have computed. Now what is this? Now we have computed it in this way. Now see, let me write now out of all these. Now we can write it in this way, that rate of change of the cost function with respect to W00 and then of layer 2, it turned out to be the error component at layer 2, the 0th error component of layer 2 multiplied by the activation 0 of layer 1, isn't it? This is 0th component of layer 2, error layer 2. That's what we have computed here. You see, it is a vector. So the 0th component of this vector is this multiplied by the corresponding input through which this weight is is linked to it. So it is A01. So A01. So now if I ask you the same question, like without doing the math, now we can directly write what is the rate of change of this cost function with respect to W00, sorry, not W00, this time W01 of layer 2. That is, now we are asking this question: how much the cost changes if I do a small change here in this weight? Okay, so what is that? That is equal to up to this point the error is same. So whatever that error is, DE0 of layer 2, same thing, same error is basically propagating through this line. You can think that way. So that error multiplied by, now if we're computing now it is the question like how much this Z changes with respect to this weight. It is proportional to A11. So you can write like A1 of layer 1. Here it was A0 of layer 1. It is A1 of layer 1. That's the only thing that's changing. Now what is this then? Rate of change of the cost function with respect to W2 of W2 of the weight of the 0th neuron, itself, but which is coming from the second neuron of the previous layer. So it is same. Now it is the error component is same. So it is DE layer 2 error of the 0th component, which should be multiplied by the corresponding input. Corresponding input is, it is coming from A2 of previous layer. So it is this. Clear, right? Now see again, now just let me write down the term. Things will boil down to one equation. And then now can I ask the same question? Now what is this? The rate of change of the cost function with respect to, we have computed these three, see, W00, W01, W02 of layer 2. With respect to this tree you have computed. Now I'm going to compute with respect to this tree. Okay, you can say like by the the beauty of mathematics, they should be very much similar. So this D0, what is the rate of change of the cost function with respect to W? Now neuron 1's weight, which is coming from the 0th neuron of the previous layer. That is this neuron 1's weight, this weight which is coming from the 0th neuron of the previous layer. How much the cost function changes if I do a small change here in this value here? Okay, So here now see, the error will be at this point, up to this point, whatever the error, the same error will be propagated through all this. So this error term will be like rate of change of the cost function with respect to these these a1 and with respect to this z1, which is nothing but de1, and then that thing, what is the rate of change of z1 with respect to now these individual terms, right? So you can think it of like this. Let me write it slightly different way. Rate of change of this cost function with respect to, or here let me write it, because there I just want to write the result. Okay, I want to compute now rate of change of cost with respect to dw10, which is equal to, I mean, dw10 of layer 2, which what you can do is that it is the rate of change of the cost with respect to that I'm trying to compute. You can do it directly. Rate of change of the cost with respect to z1 with a small change in how much the cost function change. It is basically like, yeah, that ultimately the same thing it will turn out to be. It is same as how much the output changes with respect to, I mean, how much the cost changes with respect to output 1, how much the output changes with respect to that with respect to the input to that output is generated by z1, so z1 of layer 2. And this is these two terms, if you multiply, you are getting actually de1 of 2. Okay, that is the error component of the first neuron of layer 2. This is de1 of 2. You can verify that. Okay, and that thing, ultimately the same result will come here. So it is now de1 of layer 2. That's what I already have written it. So that much multiplied by, now this much multiplied by what? How much the z changes, how much z1 of 2 changes. I mean, how much now z1 2 changes with respect to whatever it is that we want to compute it, w102, right? w10 of layer 2 of layer 2. So it is this d of w10 of layer 2. That's what we want to now find out. What is this? What is, how much, see how much this g changes with respect to this particular weight. If I do a small change here in this way, how much that z1 to or g1 of layer 2 will change? See, g1 of layer 2 is the sum of this one into the corresponding input plus this one into this input plus this one into this input plus this bias. Now see, ask this question. If I do a small change here, will it change anything about this product? No. If I make it like 100 times bigger, then also this a1 into w112, that will remain same. It will not do any change about this product. So rate of change of this thing with respect to this, I mean, the rate of change of this product with respect to a change here is 0. Rate of change of this product with respect to a change here is 0. Rate of change of this bias with respect to this weight is 0. So only thing that depends now is how much, if I do a small change here, how much this z will change. It will be proportional to this particular number here, right? So a0 of layer 1. Okay, it fits there, I mean, somehow. Only thing is this number is changing. Now let's see, what is the rate of change of the cost function with respect to w2's first neuron, but coming from input is again the first neuron of the previous layer. It is this. If I do a small change here, how much the cost function will change? It is same as like error is up to this point, it is same. So up to this point, the error is same. So rate of, I mean, this is the error of layer 2, neuron 1, multiplied by, then how much this change with respect to this particular weight. You know by this time that, okay, if I do a small change here, these are all no, they are not dependent on this one, so they are all 0. But this term will, I mean, since it is multiplied by this a11, so rate of change will be proportional to a11. So it is a11. Okay, and then similarly, rate of change of the cost function with respect to dw of neuron 1, of neuron not 1, of neuron 1, yes, of neuron 1, but it is coming from neuron 2 of layer 1. This is the thing. If I do a small change here of neuron 1, which is coming from neuron 2 of layer 1, how much that? That thing is equal to whatever it is the error, that is layer 2 error 1 component multiplied by the corresponding input a to 1, corresponding input a to 1. Okay, if you see now these equations there, I mean these terms there, like these 6 terms there, like can you see something there? Okay, now let's see what we have computed. First thing is, let's see what we have computed. We have computed how much we want to change this, right? It means initially we decided now what are the things that we have to compute. So you can see that from here we can say like, okay, we have computed actually this term, this vector, I mean sorry, this matrix. Let me copy this matrix. We have computed, now we have done our computation about this matrix there. Like, is it so? I mean, at least we have computed all the components of that matrix, but is it exactly the matrix? I'm not sure. Let's see. This thing. Now, rate of change of 0, 0, this term, and then it is 0, 1 is this term. Yes, okay. 0, 2 is this term. 1, 0 is this term. 1, 1 is this term, and 1, 2 is this term. Yes, it means what? We can put this value in the form of a matrix. But is it useful? I mean, anyhow, we are computing each individual component there. Like, you don't think that we are performing some matrix operation? I'm just saying that you can arrange these numbers in this matrix format, but it will be better if we can directly compute this matrix, right? Instead of like computing each of these terms individually, can we compute this matrix directly? Let's see, is it possible? Now you see this thing from here, can we derive something? Okay, if it is not clear, then ultimately see this dw00 is what? This particular term, no? So let's write all the term there in this matrix. So ultimately this matrix we want to compute, right? We want to compute de0 multiplied by a01. That's the first one. The second term we want de0 of layer 2 multiplied by a11, this second term I'm writing, and the third term we want de0 layer 2 multiplied by a21. Okay, there's the third term. And then similarly, let me write first de12 multiplied by a01, comma, here this term I'm writing de1 multiplied by, sometimes I'm writing dot, sometimes I'm writing multiplication. Here you just don't worry, same thing. Here it is multiplication, same, dot and multiplication right now. de1, and then it is a11, comma, and then the third term is, I'm writing comma in a matrix representation. We don't write comma, just to show you that okay, that is one term, another term, and then another term. Yeah, de2, de1, and then 2 multiplied by a2 and 1. Okay, now let's see if we can do better, or what rather my point is that, okay, can we find a way to compute this matrix from some of the results that we already have computed? Okay, that is, if we can do that, then we'll be actually computing all these terms in a single go, rather than computing these terms individually, like this one first, then this one first, and this one first. I think there's a way that like we can directly compute this matrix from some of our previous results. Okay, let's see how we can do that. One hope that I can think of is like, see, since they are like, I can think it of like, it is this matrix has 3 columns, no, like, and in each column this a0 here, it is common, this part is common, this part is common. I can do it in this way. Let's like hope that if I somehow arrange them, all of them in a single object, like a11 and a21, this is my one matrix that has 1 row and 3 columns. Okay, and then what I see is that in the first the output that we want, whatever that output that we want, suppose this is a matrix I'm considering on the left hand side, I want to multiply it, and then if I see these 2 terms, I'm taking like some part of this one and then another combination of this one. You can think it of like this combination of this and this much of this. I now from my intuition, what I feel like is okay, And obviously I did it a lot, many times also, when I did practice and everything. But first time when I did that, obviously it was driven by my intuition, and I felt it like that only. DE0 of layer 2 and DE1 of layer 2. Okay, now if I think now this is another matrix, and I multiply these two matrices, and this is, see here, this is 2 rows and 1 column, 1 column and 3 rows. So if you multiply these two, you should get a matrix that is actually, that should be of 2 rows and 3 column, and it has this 2 rows and 3 column is there. And you see each component now, D02 multiplied by A10, that is this first term. Then the second term is, again, see, this much of A0 is this thing, and nothing is there, only this much of A0 plus something else of something else is not there. Nothing down there, nothing on the right hand side there, right? So you don't have to go anywhere. So this much of this that gives you the first term, then this much of this that gives you the second, this particular term, then this much of now this activation, this other activation there of the previous layer, that gives you this. Then this much of the same activation gives you this, right? So if you see, if I multiply these matrix by these matrix, I'll get this matrix back, right? And our goal was to compute these matrix. Our goal was to compute these matrix. And then we found a way. Then see why I say I found a way, and we don't have to compute these terms like individually. Rather, what we can do is, see, this is what actually, this is nothing but this DE0 of layer 2, DE1 of layer 2. This is the error vector, right? I said it by this name. This is the error vector of layer 2. It has 2 components. And what about this matrix multiplied by, what about this A0, 1, A1, 1, A2, 1? These are the activations from the first layer, right? It is the neuron, the activation 0 of layer 1, activation 1 of layer 1, activation 2 of layer 1. Only thing is that this time they are arranged in the row rather than in a column. So you know what that thing is called as. Now that thing is called as, see, this is basically, you can say this is the activation of layer 1. See, activation of layer 1 is a vector, and that vector contains, see, this is the activation of layer 1. Activation of layer 1 is this, that has 3 components: activation 0 of layer 1, 1 of layer 1, and 2 of layer 1. That's the same thing. And see, 0 of layer 1, 1 of layer 1, 2 of layer 1. But the only thing is that this activation of layer 1, but it is written in transpose form. That is, the same column vector, first convert it to row vector, then it will be a matrix. You can consider it as a like 3 cross 1 matrix. And then on the left hand side, multiply it with the error vector, or considering it as a matrix, then you'll get, whatever this product is, basically, that is, this product will give you this. And what is these terms? These terms are like this rate of change of 0 0, weight 0 0, weight 0 1, weight 0 2, and all, and that is nothing but dw2. So ultimately at the end, when we had to compute this dw2, computing dw2 means we are computing a matrix where each components are this. See, the first 0 0 0th row, 0th column is the rate of change, or it is the amount or the proportion by which we want to change that particular weight. Okay, and it is this proportion by which we want to change that particular weight there, right? So this is a matrix. You should understand that this is equal to what? It is whatever the error vector at layer 2, whatever this error vector d0, d1 component error vector we have computed. And see, that error vector we have computed. See, this error vector we can compute from the output generated by the network, from the known output, and whatever that vector, and multiply that vector by this other vector, which is the which we get by applying the derivative of the activation 2 function there on the intermediate result of layer 2. That's also we have already computed, because see, that intermediate result of layer 2, this z0 z1, we already had computed it, right, before reaching O. So we when we reached there, we had already all these O, all Y, and all these Z's, whatever it is needed. So from O, Y, and this Z, we can compute this error. Clear? Once we have that error in that step, then the second step what we will be doing is, and once we had that error, you see, once we had that error, immediately we have like how much we want to change in B. That is how much we want to change in B means immediately we can compute from error, we can compute this. Okay, and then we tried to compute. Now we were like trying to compute this. Now this also turned out to be very much computable just by doing some matrix operation, and that is nothing but this dw2 is nothing but, it turned out to be whatever it is, this error vector that we have computed, multiplied it by with this whatever the activation of the previous neuron, and then you take it transpose. Now see, activation of the previous neuron and transpose, it is also already computed, because like we did that move, did that sorry, forward pass, and then we are now coming back. So during that forward pass, we already had computed all these values. These z's, if we need, we have it. And if we what are the activations of the layer 1, this also we have computed. During our forward pass, we computed those activations, so we have it now. Right now, when we're doing this backprop, those results are always with us. So just by now, see, what we're doing is we are multiplying this vector by with the transpose of this vector. As soon as we do that multiplication, magically now it computes the rate of change on all these weights. Not magically, obviously just by the laws of mathematics. But you see here, just by it is as if like we are multiplying only two terms, although those two terms contains a lots of internal terms. But in general, you can think it of like, okay, we are just doing a multiplication of one column vector with one row vector there. One column vector means this error. No, sorry. One column vector means this error column vector with the transpose of this means it's a row vector. Just by doing this into this, somehow we are computing all of them in a single go. That's the beauty of mathematics, I guess. And then really that is interesting thing. Now maths allows us to it allows us to describe things in a very, very compact way. There is this famous channel I follow. The two channels I think it is I find it interesting. One is this Lex Friedman's podcast, and the other one is Royal Institute Talk, where people like scientists mainly talks about their invention. And both these two channels are very interesting, and you'll find common people there, like from Royal Institute Talk. Then let this Lex Friedman, he does like interviews with different people, like philosophers, scientists, even criminals, and yeah, criminal in the sense like who were sentenced for many years, who were behind the bars for many years. But anyhow, he talks with all these people, and there somewhere I have like I remember it like mentioning many famous people there, that you can write the laws of physics in on a single paper or on the back of a t-shirt. And that's the beauty of a math. See, laws of physics that describes all these universe, all from these, from these black holes to these, small particles, everything you just can write on the back of a t-shirt. It means obviously that's something, isn't it? That's the beauty of math. I was deviating from my talk. Okay, now no problem. Okay, now we have computed the error or the amount by which you want to change this W2 matrix. That's also done. Okay, now let's see what are the questions we have already answered, or what are things that we had to compute and what are things that we already have computed. So we had to compute, these 1, 2, 3, 4 matrices we have to compute, and we already have computed up to this we have computed, this we have computed during our back propagation. We are now doing back propagation, and we computed like how much we have to change all this B0 and B1. We computed it. How much we have to change all these 3 and all these 3, we computed it. And when I say we computed it not in terms of like single element, we just computed it in general, like from the last layer. How do you update the weights? It's because I'm saying it's general in the sense that here nowhere we're assuming like a specific weights or nothing, or what is the dimension of this weight matrix, nothing. It's whatever it is, whatever this error vector is, and you take the transpose of this activation of the previous layer, multiply it accordingly, it will compute the gradient of all the weights. That's a general thing, right? I guess if people appreciate that, and you will see it, like, as again I'm saying, like when I'll be writing the code, you'll see, okay, that's true. Okay, now once we have done this, now what's the next thing is that we either have to compute B1 or we have to compute W1, DW1. Now we have crossed one layer, you see, we crossed one layer almost. I mean, see, we did that. How much we have to do this here and here, we did that. Now our turn is now how much we have to change these B's of layer 1 and W's of layer 1, right? We did B's of layer 2 and W's of layer 2 are done. Now B's of layer 1 and W's of layer 1. If we can do that, our task is done. Okay? Okay? Now, so let's now try to do how much we want to change this first one, and if we can do this properly, wholeheartedly, going through the details, then computing rest of them will become very easy. Okay, I mean, computing rest of them by this way, I showed this way, that is obviously not visible. Computing rest of them will be very easy. Okay, now let's see, how right now focus on this point, that now we want to compute what is the rate of change of the cost function with respect to B0 of layer 1. That is our question, and that is what we want to answer. Let me copy this network down there one more time. Okay, so we have to compute the rate of change of the cost function with respect to B01. It means we have to compute the rate of change of this cost function with respect to B01. Okay, now it seems like, see here, the question is that, see, if I do a small change in B0, then how much this cost will change. Now see, if I do a small change in B0, then if you follow the path, then you'll realize that, okay, if you do a small change in B0, see, if you do a small change in B0, that will do a change in Z0 of layer 1. If I do a small change in B0 in layer 1 here, then it will do a small change in Z0 of layer 1, which in turn will do a small change in the output of the activation function of layer 1. Activation 1, this is 1, not prime. Activation 1, that activation function of layer 1. So it means it will change this, the output of that activation function is nothing but, we have written it like A01. See, if I do a small change here, it will do a small change in Z0. If I do a small change in Z0, it will means that small change in Z0 will again do a small change in this particular output here, A01. Up to that point, it was a single line, no problem. Now, but from there, you see, from there, like two parts. This error here, I mean, this change here will do a change in, through this line, it will do a change here, and through this line, it will do a change here, isn't it? Now, from there, it is as if like now it will branch now. That, okay, from there it will do this, it will do a change in, now see, using this part, it will do a change in what, it will do a change in this product. Ultimately it will do a change in Z0. It will do a change in Z0 of layer 2, which again it will do a change in A0 to, means this thing, neuron of 0, activation of 0 of layer 2, which will again do a change in output, but basically they are the same thing. In turn, it will do a change in cost. It will do a change in cost, right? But the other part is also possible, isn't it? A small change here, it will be propagating through this line also, which will change this Z1 of layer 2, which will again change this A1 of layer 2, which will again change the cost. These two costs, there are no two costs, this is the same cost there, right? So the cost, the same cost, will be influenced by two different parts if you do a small change in B0, and that is the case with not only B0. If you do a small change in W00, that you should realize that that will also be propagated through these two parts to the cost. If you do a small change here, that will also propagate it through these two parts to the cost. Now, these parts will be the same. I mean, for not only for B0, for W001 and W011, the change in these two also will go through this Z11 through this activation, and then again from here it will take two parts there. Are you getting what am I saying you? Right? Now see, if you might be thinking, okay, that is quite complicated. I mean, if we now simply at this moment, if you think of like, okay, you are now only 2 layers away, so you have 2 different paths. So if you are like, 4 or 5 layers away, you can have like multiple different paths there, right? And based on the neurons in that layer and everything. Don't worry, we don't have to do that much of branching, because you see why we don't have to do that. No matter like how far this layer is, like it could have like, like 10 more layers after that before reaching this cost. Okay, you just can assume that, extend that. Okay, so you can think like, how many parts there, like you forget about it. But at one thing is sure, that if you now think it in terms of backprop, what is happening is that the we are like, at the end we are computing the cost, and then what we do is we compute the error there, right? I mean, cost, what is cost? Cost gives you the error of the network, and that error we propagate, like see here, that error propagates at this point. It is known as DE0 of layer 2. At this point, whatever it is the error, that is the error, no matter how many layers are there, right? We don't need to keep track of the number of layers beyond that, because we know like at this point that is the error, at this point that is the error, right? Now you see the same thing is now here, like somehow if you can compute, the error at this point, error at this point, like let's call it, say for example, error of layer 1 of neuron 0. Okay, somehow if we can compute it, then all these how much you want to change, to minimize the cost function, that thing will be determined by this error only. And no matter from how many layers this error have been propagating to this point, right? Somehow if we can compute what is this error, then we don't need to keep track of like from how many layers they have been like propagating, that error has been propagating to at this point, right? To this point. You got my point? It means this is could be this, or it could be like there could be multiple branches also, like before actually reaching the cost, say this cost there, there are like multiple branches through which all these errors are propagating, and at some point of time they will accumulate here. See, this is the junction sort of. Now here in this example, let's concentrate what is happening. We know what is this error here. Okay, let me show you with some color. Okay, now see, what I mean is that you know what is this error here, right? You know what is this error. I mark it, say, with blue color. Now this is the error at this point, and you also know what is this error here, right? These two are two different error terms, like one propagated through this O0 channel and another one is O1 channel of the total error. Okay, don't get confused at this point. Like we know these two terms are computable. We have already seen that. Now see this blue error. Now it will propagate through this channel. I mean, through this channel, you can think it of like it will propagate to this particular. It will propagate through this channel to this. Some error will accumulate here through this channel. You got my point? What I'm trying to say. You just intuitively just think that some amount of that error will propagate to this point, right? That yellow error, and then some amount of this blue error also will propagate through this channel, through this path. It will propagate to this point, right? So at this point the error is nothing but it is the error over like which came through this line, and then the error through which came through this line. Okay, it is the total error there. Got the point? Now, what is that total error? Obviously, you have to compute it. And then if we multiply that total error, that blue plus yellow, multiply that total error with the derivative of this activation function. That is, if we pass that error through this activation function in the backward direction, which is nothing but multiplying this error by the derivative of this activation function, then we get this DE0. DE0 will be a combination, or it will be a like somehow it will be a combination of this yellow and blue part. Now here some portion will be yellow and here some portion will be blue. You should realize that point there. Okay, that DE0 will be somehow it is a total error which is accumulated at this point. So if you can find a way of computing the total error which is not dependent on how many layers are there after this layer, then it's fine. You can do that. Okay, got it? that is one way of showing you the thing. Now let me tell you if I can do better here. Now our goal is that one point I just tried to convince you people that somehow we have to compute this error here. Okay, now let's use our the chain rule to try to compute rate of change of the cost with respect to B01. Okay, we want to find how much this changes with respect to this. Okay, so I can write it in this way. Can I write it like rate of change of the cost function with respect to rate of change of the cost function with respect to the output of layer 1 0 neuron? Directly I'm computing how much this changes with respect to a small change here. Okay, I am not considering like how many layers through which it has propagated. No, I just I'm thinking that okay, this term is possible, and then once it is done, once we can compute this, then we can compute this also, which is nothing but how much this activation 0 of layer 1 changes with respect to a small change in Z0 of layer 1, which is nothing but what this is saying is that what is this activation 0 of layer 1? It is the output of this activation 1 function, where you give Z0 as the input. So it is basically asking you this term is nothing but it is asking you what is the rate of change of the activation 1 function. What is the rate of change of the activation 1 function when you give input Z0 and with respect to a small change in Z0? That is, if you do a small change in Z0, how much the output of this activation 1 function will change? Are you getting what I'm saying? That's what this term is computing. Okay, and then now if you multiply this thing with this thing, you get the product of these two. You can think it of like that is the error. Now that is the product of these two. You can as a whole you can say okay, that is the error at neuron 0 of layer 1. Okay, got it. Now this thing, okay, fine. And now forget about B1. I mean, if you want to compute what is this rate of change of cost with respect to B1, now once you have this term DE0 up to this point, if you know the error, then it is just multiplying that thing with the rate of change of Z0 with respect to B0. Okay, so these two I'm representing as this. And then if you are interested in this, then you have to compute this also. You have to multiply that thing with rate of change of this Z0 of layer 1 with respect to B0 of layer 1. And by this time you know what is that, because you see, if I do a small change here, how much this Z0 will change. I'm just taking the easy case first. Okay, just forget about everything, just try to answer this question. How much this Z0 will change if I do a small change in B0? Okay, what is Z0? It is the sum of this one into this one plus this one into this one plus this one. And see here now, okay, it's just like this. No, instead of saying, just let me do it. Rate of change of W001 multiplied by this one multiplied by A0 of layer 0 plus W, this one now, W01 and 1 multiplied by this one multiplied by A10, and then plus this bias term here is there, bias 0 of layer 1. We want to compute how this thing changes with respect to a small change in B0 of layer 1. Okay, and you know that like this term doesn't change, so 0, this term doesn't change, 0, B01 with respect to B01 is equal to 1. So this term is equal to 1. Okay, this entire term is equal to 1. Okay, next time I'll not derive it, by this time. I think I'm making you people bored. But anyhow, that you have understood. But and also this term we are computing as DE0. But still, I didn't tell you what is the actual expression of computing DE0, because we don't know this, no? Although we know like what is this derivative of the activation 1 function, we know that, but we don't know what is the actual form of writing rate of change of cost with respect to A01. This we have not yet computed. But if we can figure out how to compute this term, then all the things are done, huh? So okay, now see here, before actually computing this, what is this before, now see, our focus is on this particular term, huh? I mean, you need to know how to compute this, okay? And let's see how to compute this. Okay, before proceeding further, let's see how to compute that. Okay, forget about all the thing. Now our goal will be, we want to compute how much, our goal will be now directly to compute what is the rate of change of the cost function with respect to the activation 0 of layer 1. That's all, that's our goal. Okay, that's our goal, activation 0 of layer 1. Let's see how to do that. Okay, now what is that, what is this, I mean, what is the rate of change of this function with respect to this? Now see, there is no branching. I mean, we just removed from our, you know, computation or calculation. That part is not important now. What we want is that how much this cost changes if I do a small change in A0, and it is the sum of both the thing, like whatever the, you know, whatever the change is made by this part plus whatever the change is made by this particular part. You see that? You see that? Okay, okay. Rate of change of this cost, rate of change of this cost with respect to, so okay, just try to take one part at a time. Okay, rate of change of the cost with respect to, say, O0 first, or O0 in the sense with respect to A02. Rate of change of the cost with respect to O0 will also find. Rate of change of the cost with respect to O0, that's this term. How much this changes with respect to this, because these are two parts, no? Like this is one part through which it will propagate, and this is this other part through which it will propagate, right? So rate of change of the cost with respect to O0, and then how much this O0 changes with respect to Z0, how much this rate of change of the O0, how much that changes with respect to Z0 of layer 2, and then how much this Z0 of layer 2 changes. Now what is this here? See how much this cost changes with respect to this, how much this O changes with respect to Z02, and then how much this Z0 changes with respect to what then? With respect to how much this Z0 changes with respect to now this A01, right? That's what we wanted, right? I mean, see, now this Z0 directly depends on A01, so you can write it. So let's write it. How much this thing changes with respect to a small change in neuron 0's activation of layer 1. That's what we want to compute. And see here whether it is right or wrong, just you can verify it in this way. DO0 cancel, Z02 Z02 cancel, so it is DC by DA01. That's what, DC by DA01. That's what we want to compute, right? But that is only through one part. Now the other part also, how much the cost changes with respect to the other output there, like other component of the output. Cost changes O1 through this part. Now we want to write, okay, how much this cost changes with respect to the rate of a small change in this output, and then how much this output changes with respect to a small change in the Z value of neuron 1 of layer 2. That is this term here, like Z1 of layer 2, you know, how much this output changes with respect to this, that is how much this changes with respect to, you know, a small change in Z1. Now see here, output is a function of activation. It is the output of the activation function. So basically here we are asking how much the output of the activation function changes with respect to the input to the activation function. Okay, and then what we want is how much then that input to the activation function changes of layer 2, which is nothing but this Z12, with respect to what? With respect to what we are computing? With respect to, now we are computing it with respect to this particular neuron there. So you see here this neuron. So it is A0, that is if I do a small change in the neuron 0 of layer 1. And these are the only two possible paths possible. These are only two parts possible, right? Okay, now see, you might be thinking, so anyhow I used only two terms there, so it means I'm making some assumption about the number of layers which through which it is, you know, propagating back. Yes, if you see it that way, it is okay, it is true. But now what we can do is I can eliminate that, the concept of propagating, from how many years it has been propagating. Because now see this term, what is this term is like change of cost with respect to output and output with respect to z0. See, change of cost with respect to output, then output with respect to z0 is de0. It means it is the error from this layer and this layer. This is it is the error, like, see here, this neuron is connected with this neuron. So whatever it is, this error here, no matter from how many layers it has been propagating, that's irrelevant. Now whatever this error, that is only matters, right? So this thing is nothing but what? This is de0 of layer 2. This is de0 of layer 2, de0 of layer 2. And similarly, what is this term? What are these? What are these product of these two terms are the rate of change of cost with respect to O1 and O1 with respect to Z1. Cost O1 with respect to O1 and O1 with respect to Z1 is this DE1 there, right? So DE1. So this term is DE1 of layer 2. Now this plus is also there. Now this is this error. So it means what we're doing is basically we're computing the rate of change of the cost function with respect to A0 when we tried to compute it, which we saw like, okay, there are two parts, this part and this part. And again, you see here, this term is D0, that is, this is this blue term propagating back, this is this blue term propagating back, and this is this yellow term propagating back. No, so this is this blue term, it will propagate back, and this is this yellow term which will propagate back. Okay, we have written it that way. And then now what about this term? What is this this term and this term? Okay, so we know, like, we don't have to compute it because we already have computed this term. We don't have to compute this thing because we already have computed this thing, right? So this we don't have to recalculate. Only thing is that what about this? So let's try to do it here. What is the rate of change of Z02 with respect to the A01? The question is this: if I do a small change here, A01, any means, by changing B0, maybe by changing this one or this one, but any means, if I do a small change here, how much the Z0 function will change? Okay, that is how much this value will change. That is my question. If I do a small change here, how much this will change? Okay, now let's see. It is quite obvious now. It is the only one part. You see, if I do a small change here, certainly that change will change this one also, but our question doesn't involve that right now, right? Our question is that how much Z0 will change. Explicitly it is asking how much this value will change if I do a small change here. Okay, only this part we are talking about right now. Clear? Clear. Okay, now what is that? Directly we can expand it. Why we can expand it? Because we know, like, Z0 is, we can write in terms of, it is directly dependent on A01, right? It is this way. What is Z02 is equal to? It is, what is Z02 is equal to? Z0, I mean, this term is equal to, you see there are like 3 inputs it has. So let's write them all. So it is W weight 0 of neuron 0, I mean layer 2, multiplied by neuron 0 of layer 1 plus weight of neuron 0 coming from neuron 1 of layer 1, and this is layer 2, and this is neuron 1 of layer 1. Okay, and then plus W0 neuron coming from the second neuron of the previous layer of layer 2. I'm talking about that particular weight multiplied by, since it is coming from neuron 2 of previous layer, so neuron 2 of previous layer means the current layer is 2, previous layer is 1, neuron 2. You will write it that way. Okay, and then plus we have to add a bias also, and bias means bias of layer 2, bias of layer 2. And which neuron we are talking about? We are talking about the 0th neuron of layer 2, right? That's what this term is, you see. Okay, every time I have to do scroll, so let's copy this. Okay, just to avoid scrolling, I wrote both of them now side by side. Now you see what we just saw. We want to compute how much this Z02 changes with respect to A01. That is how much this term changes with respect to this term here. And that turned out to be, like, what is this Z02 term? It is W002 multiplied by A01. Let us see, W002, this weight multiplied by this input, plus W01A1, it means W01 of layer 2 multiplied by A1, plus W02 multiplied by A21, W02 multiplied by A21 plus this this into this plus this into this plus this into this, plus what we do, we add this bias 0 of layer 2 here, right? Bias 0 of layer 2, that's all. And then we want to find the derivative of this with respect to A01. Okay, A01. Now you see what is that. Now you see this A01 term is only it is here, but it is not here. It is not A01, it is A11. Nowhere A01 you will find. Or another way of thinking it is that if I do a small change in A01, will it change anything about this product A11 into W012? No, nothing. It will not. If I make it very big, very small, this product will remain same. Similarly, if I do a small change here, it will not change anything about this product. So these terms will not change if I do any change in A01. Similarly, this bias is also not going to change if I change anything in A01. That is, any change happens here doesn't affect any way this particular bias, right? So it doesn't change. So rate of change of this is 0, rate of change of this is 0, rate of change of this is 0. Okay, so what we left with is, it is nothing but rate of change of W002 multiplied by A01 then with respect to A01. And it is like AX with respect to X. So it is now, see, it is AX. This time the role is changed. Now W002 became the A, and this A became the X. No, it is like, see, this A01, it is same. So this is the constant here. So that will be the the rate of change of Z0 with respect to A01. So this is actually this particular weight 002 through which this A01 is multiplied with. So when we were computing how much this will change with respect to this, it is actually whatever it is the weight through which that input is multiplied by. So it is multiplied by 002, so it is 002. But anyhow, that's the thing. Got it? Okay, now where were we? We were trying to compute DZ02A02. That's what we have computed. And what is that? That is nothing but the weight, the corresponding weight through which it is connected with that neuron. So it is 002, W002. Okay, done. Now what about this rate of change of Z12 with respect to A01? It is asking you the same question, but with respect to now this Z value, not this Z value here, the second one, but with respect to the same neuron. Okay, so if you want to compute, you can compute it, or you can directly, but just by looking at this, you can tell it. But okay, let's compute it. What is the rate of change of what is the rate of change of Z12 with respect to a small change in A01? That's what this thing is asking, right? Z12 with this, right? And what is that? That you will see now. That derivation I might not do, huh? Now see, it is the same question, isn't it? I mean, okay, let's do it. If you expand it, it will look like, what is Z12 is? It is nothing but the weight 102 multiplied by, that is this weight multiplied by A01 plus weight 1 of layer 2 multiplied by activation 1 of layer 1 plus W12 of layer 2 multiplied by the activation 2 of layer 1, plus we have to add the bias 1 of layer 2. That's what is this Z12 is with respect to the A01, isn't it? See, W122 into A2. This is W12 into the corresponding A21. This input is multiplied by this input weight, and similarly this input is this weight, this input is that weight, and then we add this bias B12 there. That's Z12. That's Z12, right? And then with respect to A10, what is the change, rate of change? And then again, by applying now using the same concept, you can see that rate of change of this is 0, this is 0, this is 0, because A01 term is not here, so it doesn't change, only this term. And here we are asking like DAX, this is your X now with respect to X. So A is your W10, 2. Now see how much this Z changes with respect to A01. It is same as whatever the weight by which that A01 is multiplied with. A01 is multiplied with by W102, so it is W102. Okay, got it? Okay, done. So we have computed it. That is W102. This thing is W10 of layer 2. That's all. That's we have computed the rate of change of the cost function with respect to A01. Now it is the sum of this blue line. It means, you see, the error, this blue error multiplied by this weight. You see now, this blue error. Okay, if it is not clear, let me draw it blue. So this blue error, what is this term? This term is this blue error term, right? This blue error term, DE02 is this blue error multiplied by weight 002. That's weight 002. Whatever it is, this term, it will accumulate here. That's the first term, right, of this summation. This entire term I have written here as blue, but you know, say blue into this thing is equal to a blue term. This thing is equal to this into this, okay? And then this other term, yellow term, is also coming from the other direction. This yellow term, DE1, that is this yellow term here, right? This yellow term multiplied by the corresponding weight, through which weight it is propagating back to A01. It is propagating back to this weight, and if you see, that term is W102. That is this W102. So it means this yellow term multiplied by this is this small yellow. This blue term multiplied by this is this small blue. I have written it that way, and that blue plus yellow is the total error at this point, right? At this point, this is the total error, and that I'm writing as rate of change of the cost function with respect to DA01. DA01. It means how much the cost function changes with respect to DA01 is like, it is the error in the next layer, DE02, because see, we are talking about neuron at layer 1, so we are multiplying it with by layer 2's error. You see, these terms are fixed, 2 and 2, 2 and 2. It doesn't depend on like how far it is propagating back, because we are just computing from there here. Like if we are computing the error at this point, we are considering, okay, whatever the error of the previous layer's neuron, and through whatever the path it is coming, we are just multiplying the weight with it, and then we are getting, okay, this much will accumulate here, this error will accumulate here, this much. Got it? I think things should make sense here, I guess, huh? So you can pause the video if things are not clear, then again you can resume. But now that is what we have computed. Okay, let's now continue further. What we want to do is, okay, we have computed this. Now same thing, now we want to repeat, like how much this let's first compute it. This is a good term, no? How much this A01 changes with respect to, or how much this cost changes with respect to A01, and then or ultimately we wanted to compute the error at this point, so we'll be multiplying this term now with the activation function, or the derivative of the activation function of this, then we'll get this particular term. So, but before that, let's see here, let's first compute these the sum of these blue and yellow part for all these neurons there, okay? Because you see, for all the neurons there will be a blue and yellow part, isn't it? Because now see, this yellow error will propagate through this channel, I mean this particular part, and it will accumulate some yellow here. That this blue error will also propagate through this channel also, or this part also, so they will accumulate. So this blue and yellow error will accumulate here also. The same thing, this yellow error will follow this part, and some yellow error will be here, and this blue error will propagate through this part, and some blue error will be here. So let me draw that yellow, and then this yellow will propagate through this, and it will have some yellow. Let's first compute the sum of this blue and yellow, blue and yellow, blue and yellow for all these activations there, okay? Already we have computed for the first neuron. We'll be doing it for the other neurons, okay? So that will be our next step. Let's do it. Okay, for simplicity, I copied this above derivation here again. Now we want to compute this. You see, rate of change of the cost with respect to a small change in activation 1 of layer 1. That's what we want to compute. Now here, this blue term plus this yellow term component we have to compute here. It is actually, you see here, what is this blue term and the yellow term? It is same, the blue error multiplied by the corresponding weight there. You see, this blue error propagated through this weight is this blue term. So what is that blue error? We already have computed. It is DE02 multiplied by propagated through this channel or this weight, you can see W012. So this is W01 of layer 2. So through this part, whatever the error, this is this. So this weight multiplied by this error is this blue error here. And then similarly, the yellow part is this yellow error, whatever it is, that DE1 of layer 2 multiplied by propagated through this particular part here, this line here, this weight here, whatever you want to call it. So propagated through this is W112. So it is W112. Okay. And then the third term is also there. And what is that third term? What is the rate of change of the cost function with respect to a small change in the activation 2 of layer 1? That is there, here. I mean, you know, we want to compute this error now. Okay, so that error is what? That error is whatever it is, this blue part propagated through this way, this blue error propagated through this part, plus this yellow error propagated through this part, right? Clear now, no? So you just write it then. This error part is same. This blue error, this is your blue error multiplied by the corresponding weight of the part, like whatever, that W022, this weight, W02 W02 of layer 2, then the yellow error part, that is DE1 of layer 2, DE1 of layer 2 multiplied by yellow error, which propagated to this particular neuron through which weight? This weight, W12 of 2. So it is W12 of 2. So once we do all this tree computation, what we're going to get is, we're going to get the error at this point. At this point, we're going to get error. We're going to get the error at this point. We're going to get the error at this point. Okay. But we want to, now whatever that error, if you multiply it by the derivative of the activation function of layer 1, then we're going to get the error at this point, error at this point, and error at this point. Okay, so if you can compute this, then immediately you can compute that also. So we have already seen what are the expression to compute all these three. But from this expression, can we, like, now again the same way we did those matrix operation for our previous cases, can we do some, can we, instead of computing these expression individually, can we do some matrix operation that computes all these values in a single go? Let's see. What is this now? Okay, now let's see what we can do. Error into weight 00. Okay, what you can think it of, like, you can think it of like it is taking this much of error 0, then this much of error 1, and this is another combination. This much of error 0, this much of error 1. This is another combination, this much of error, same error 0, same error. So basically we are taking three combination of error 0 and error 1, and that can be written as, see, we are taking three combination of error 0 and error 1. So you see error 0 of layer 2 and error 1 of layer 2. There are two errors in layer, I guess. There are two errors in layer 2. So error 0 of layer 2, error 1 of layer 2. This is what this thing is. So let me write it in this. D is there, okay, just to be consistent. But anyhow, these two error, you can think it of like, okay, this is 1, and we want to take different combination of these errors. And how do you do that? If you think in terms of matrices, then you have to write the the combination as the rows of a matrix that you put on the left hand side. So what are the combinations we want to take? You see, we want to take like W002 much of this one. Okay, that is this one multiplied by this one. So one part is like this, W002, then this is this much of this plus 102 of E1, that much. So it is weight this one, and another the weight is like 10 of 2. So you take this much of this plus this much of this will give you the first value here. It is like W002 of DE02 plus W102 and DE, what am I doing? W002 of DE02 and W102 of DE1. DE1 of layer 2. Okay, so that will give you the first term. As soon as I put this pair, It means I'm taking this combination of these inputs to get this value here. There is a single number, and that is this. You see, D02 W002 D02 W002 plus D12 W102 W102, right? That is this term. So this term it is done. Now just now see that the second term there, then it is just a different combination. Is the combinations are like W01 of layer 2 and W11 of layer 2, right? And then that will give you, see, W012 W012 multiplied by cannot write now, DE02, because 02 this thing into this thing, D02 plus this much of this, that is W112 much of DE12. That's all. That is this term. You see that 012 DE02 012 DE02 plus D12 W112 D12 W112. So that if I put this pair here, then multiply this thing with this vector, column vector, will get this. Same way, it will be like W02 of layer 2 and then W12 of layer 2. If we take this much of this plus this much of this, we'll get this third value. Just write it. W002 much of DE02 and then plus this much of, that is W12 of 2 of DE1 of 2, then that is this term, right? That is this term, isn't it? So it means what we're doing is basically, if we multiply this matrix by this matrix, you can think of like matrix multiplication. If you multiply this you know, like what is the size of this matrix, 3 rows 2 column matrix by this 3 rows 2 column matrix by these 2 rows 1 column matrix, then you will get 3 rows 1 column matrix. That is exactly the size of this. You have see 3 rows and 1 column. It is a 3 cross 1 matrix, 3 rows 1 column matrix. Got it? So what it is actually, so it means, and now what is this W00 to W102, and is it there already? Is it the W2 matrix? What is this W2 matrix? W2 matrix, you see this W2 matrix, certainly this matrix is, since this 2 is there, it means it is all the, see here you can see all the weights of W2 matrix, but in a different form, right? And what is that different form? Actually our W2 matrix was like this: weight W200 W201 W202. It was a 2 into 3 matrix, right? It was a 2 into 3 matrix. It was like this initially. It is W2 of 00. It is the neuron zeros coming from the first neuron 0 coming from the neuron at index 1, and W of neuron 0 itself coming from neuron 2 of previous layer, and then this. Now here also it is W, but it is 1 neuron coming from the 0th neuron, W1 coming from the first neuron, W1 the first neuron's weight only, but coming from the second neuron. And these are all the weights of the second weight matrix. So now see, or the second layer. Now you see this was W2, and what is this thing then? You can say like 00 000102 000102. It was the first row, that the first row became the first column and the second row became the second column. So this matrix, what is this matrix then? Easily you can tell me, this is W2 matrix itself, W2 matrix, but if you take the transpose of that matrix. So W2 transpose multiplied by, what is this? D0 to D12. It is this error vector, isn't it? This error vector DE of layer 2. This is a vector DE of layer 2, or you can say it's a column vector of layer 2. So if you multiply these two, this matrix by, you already have that weight matrix, isn't it? So you have that weight matrix, you take the transpose of it, and then you multiply by this error vector, and by the time you are doing the computation here, you already had computed the error vector at layer 2. This is the error vector at layer 2, right? This error vector you already had computed. So you have all the things when you are doing this computation, when you are performing this computation, you have all the necessary thing already computed. So what basically you can do is that, okay, you can think it of like a temporary result you are computing, that is the A of layer 2, dA of layer, not 2, dA of layer 1. Okay, let's say dA of layer 1 is, that represents this, blue plus yellow part of 0th neuron, blue plus yellow part of the first neuron, and blue plus yellow part of the second neuron. And we just have seen that how we can compute this blue plus yellow part of each of these neuron just by multiplying this transpose of the weight to matrix with the error at layer 2 there. Okay, so this vector, now this vector is what it is, the weight to matrix, then you take the transpose and then you multiply it with the error 2. And you know what is this, how many components will be there? Currently, based on the size of weight and matrix and everything, it should be of size 3 cross 1, and that's fine. Like we need 3 cross 1 means 3 rows 1 column. It means we need 3 components, and we got these 3 components, this part, this part, this part there. Okay, now what we want is, actually we want that much to be propagated one step further here. Like what we actually want it to be here, because for all these, because you see here, because for all these, we have computed up to this point, right? This is this, a0, a1, a2 for all of them, and then that one step for all this b0, w00, and w01, this term is also common, so you just can multiply that thing with this, and then these are different things. Are you getting what I'm trying to say you? Okay, so for that reason, what you do is you just can compute another temporary result. Now you actually want to compute the error at now layer 1 you want to compute. You see, you are computing error at layer 1. That's what I said you here. You see, this is error at layer 1, and here also you want to compute the same term here. This is the error at layer 1 itself, but this is also the error at layer 1 itself, but of neuron 1. And here also at this point, you see, at this point here, it is the error at layer 1 but of the neuron 2. It is also the error at layer 1 of neuron 1, error at layer 1 of neuron 0. So let me just highlight them with this blue yellow color. It is this blue yellow color. This is this yellow and blue error, and yellow and blue error. Okay, got it. So let me do it this way. This part here and this part here. These 3 errors we are interested in. These 3 errors ultimately. Now these are the, see the way we computed the error for the second layer at this point. Now we want to compute the error at this point of the first layer. And if you can do that, then the error already since you know the error at this point, you don't need to keep track of like from how many years they have been for how many layers they have been accumulating through, right? You got it? So now that's the simplification. So now you see, computing that result is not a difficult job because we already have up to this point, no? So if we have up to that point, then what is the error actually? This error is nothing but the error at whatever this temporary error we have computed at layer 1, that thing multiplied by what? Multiplied by the, the derivative, activation 1, say, where did I write the 1? Say activation 1 function. This is your activation 1 function on these z values, right? What is this? Activation 1 of z of layer 1. What? All the z's of layer 1. Okay, so all the z's of layer 1. So this thing multiplied by the derivative of the activation function when we give the input as the z value, the intermediate result which were computed at layer 1. This, now this thing is a vector. Now see, as I said, no, it is a like this activation 1 prime is the derivative of the activation function through which you will be passing this z1 here. This is not prime, this you will be passing this z1 vector. So you can think it of like this particular operation will be computed in this way. See, z1 has how many components? It can have any component, but in this example we have z1 has the 0th component, the first component, and the second component. So z1 has 3 components. This z1 has 0th component, z1 has 1 component, and z1 has this second component. So this activation prime will work upon all of them. Activation prime when this and activation prime of this activation one functions prime, and that's the same thing, activation 1 prime, that whatever it is, on this. So it is like, you are applying this function on this vector. It means that you are actually applying this function on all these elements of the vector individually. Okay, so what ultimately this will give you, another vector. This is a vector, then you see. So ultimately this is a vector of 3 elements. You will get it, where each of this element, this is this, and this element is this, and this element is this one, right? And then you are multiplying it with this vector. This is also a 3 element vector. This will also be a 3 element vector, where this first element here of this vector is is the this term here, like this into this into this, and this you computed by just doing this matrix multiplication. So now don't need to go back and again trace like what was it, but this, we know that this is a vector. It will have equal number of components as this vector has. So when you do this multiplication, it is not matrix multiplication or something you're doing what? When you do that multiplication, basically you're doing like this multiplied by this one will be multiplied by this one, and this one will be multiplied by this one, and this one will be multiplied by this one individually, element wise. Okay, so that is your DE1. Are you getting what am I saying you? So we have now seen how we can compute DE1. See here, DE1 can be computed from DA1 and then the derivative of the activation 1 function. So this we know, this function we know, this Z1 also we have computed during our forward pass. So that also we know, and this DA1 also can be computed from weights, the weights of layer 2, and then the error accumulated layer 2. So all these values are there, so we can compute it when we are doing the back propagation, right? So at this point we have computed now the error accumulated at layer 1. That's what DE1 we have computed. It means we have computed the error accumulated at layer 1, means here and here and here, right? Now till now we have been computing only temporary result. Now that is useful. Now we can we want to compute how much this B0 changes with respect to the cost is same as like how much of this error you can say like it is same as like how much this B0 changes with respect to Z, and how much Z changes with respect to the cost, and how much Z changes with respect to the cost is this particular term. Okay, so let's now do it. Now let's go back, let's come to the point now let's again bring me this diagram below there so that I can read whenever I need it. Okay, now we have seen how to compute. We have computed up to this point, like this error vector we have computed. That is, we have computed this DE1, DE of layer 1. Okay, this is a vector. This is a vector that contains the D0 of layer 1, D1 of layer 1, and D2 of layer 1. This is computed as we can compute it in a single go. For all of them we can compute just by multiplying the transpose of this weight matrix by this error vector from the previous layer. If we do that, you'll magically, again I'm saying the word magically, you will get this error vector here. Okay, not exactly this error vector, but you will get this temporary error vector at these points, and then if you multiply them with the the derivative of the activation function, you will get this error vector. So I have shown you how to compute that. Now the next question is, once we have that, the next question is, now we want to answer is, what is this was our main goal, right? How much this rate, what is the rate of change of this B0 with respect to B01? How much, if how much this cost function changes with respect to this B0? Okay, so that I started wrong actually. That's why I found it difficult to say. So we want to now do this. What is the rate of change of the cost function with respect to B01? Right, that's what we want to do. And what it is like how much this cost function changes with respect to actually with respect to this Z0, the Z0 of layer 1, dz0 of layer 1, and then how much this dz0 of layer 1 changes with respect to b01. Okay, so that's what we want to find. And see here, rate of change of the cost with respect to dz01 is nothing but, you know, this error here. Okay, so it will be de01 multiplied by, what is the rate of change of this z with respect to b0? How much this z changes with b0? You know that is 1, so it is 1. Similarly, now what is the rate of change of the cost with respect to b1 of layer 1? It is b1 of layer 1. It is same as whatever it is the rate of change of the cost with respect to the, you know, with respect to the dz1 of layer 1, and then what is this dz1 of layer 1 changes with respect to b1 of layer 1. Okay, and see, this dc by dz11 is nothing but, you know, rate of change of this cost by z11 is nothing but whatever this error accumulated up to this point. Okay, so this is nothing but de1 of layer 1 multiplied by dz1 b1 is nothing but it is, now this z1 changes with respect to b1 by 1, I mean linearly, so this is 1. Similarly, rate of change of the cost function with respect to b2 of layer 1, it is equal to whatever it is the error accumulated at neuron 2 of layer 1. Neuron 2 of layer 1 multiplied by certainly this one. Okay, so that is equal to 1. So ultimately, in terms of matrix operation, what we can write is, ultimately this implies what? This vector, whatever this vector, this rate of change of the biases of layer 1 we are computing, it is same as the error at layer 1. That's what. This is the vector, this is another vector. This vector is same as this vector. So it means how much you want to change here, how much you want to change here, how much you want to change here. If you consider all those changes as a vector, that will be same as whatever it is this error here, whatever it is this error here, whatever it is this error here. It will be actually the proportional. That's why you multiply by that, you know, that proportionality constant eta there. Got it? Okay. So that's all. Then db1 we have computed. Now we have computed db1. Now our next task is, now we are like, explosion is done. Now we are like, you know, settling down. Now things will be much easier now. Now you see, now since we have computed this b1 vector we have computed. So if you go back and see what are things previously we have decided, no, what are things we have to compute. So we have now finished computing this also. We know how to compute this one also. We computed this. Last is, how do we compute this? And you see, it will be quite beautiful actually. And it will be quite symmetric. It will make perfect sense. Now, what we want to do is, we want to compute now the rate of change of the cost function with respect to all these weights. This one. How it will do that? It's easy, no? It's same. Because you see, we already did that. I mean, if we know the error, if we have this weight matrix, if we know the error and we know the activation of the previous layer, then we can compute how much we have to change these weights. Here also we know the error, we know the activation of the previous layer, then we know how to change these weights here, isn't it? So without doing any calculation, just make a guess now what it will be. It will be like this. You see here, we want to now compute this vector. Let's say we want to compute this W, how much the weight of W1 matrix we want to change. So this is this one. Oh, sorry. This is this one. Okay, this is W1, and let me write it as like, this is equal to, okay, so how much it is. So let's first write it like in this way. It is like, whatever it is the change that I want to do in this 0 0 component. So 0 0, this is not a computation I'm doing, I'm just expanding that matrix. That matrix should have these elements. So whatever this matrix says that, okay, what are the changes that we want to do in W1 matrix? So I'm writing it, okay, this is equal to whatever it is the change that I want to do in this particular weight there. and another column will be whatever the changes that I want to do in this particular weight there, 0 1 of 1. Okay, and because at the end we want to add this dw1 vector, or we want to, like, subtract this dw1 vector from, dw1 matrix from w1 matrix, so their sizes must be same. So if w1 is a like 3 cross 2 matrix, then it also should be a 3 cross 2 matrix, where each row will represent the weights of the corresponding neurons. So the first row represents the weights of the first neuron, second row second neuron, third row third neuron. So it will be like that only, right? This is w01, the first neuron of layer 1, and whatever the changes I have to do with the weight of the first neurons, weight coming from the first neuron of the previous layer. This one, just this is w20, this is w also, this is also dw20, but this is also layer 1. What did I do? I'm sorry. 2's neuron 0 0, and this is 1 actually. It's coming from layer 1. Now what are these terms? Now what you can think it of, like, how much we want to do these changes, that now we have to, like, focus here, like, what is this term? If we can somehow derive that, it will make sense. Now we can do that, no? Okay, since we have done so much similar things so many times now, I think if people can do it directly, okay, then also it's a good idea. I mean, this basically is saying that how much this what is the rate of change of the cost function with respect to w001. That's what this term is equal to. Okay, again, I'm not doing any calculation, I'm just writing different version of the same thing, no computation I'm doing. Now rate of change of the cost function with respect to a small change in 0 1 1. Same thing, rate of change of the cost function with respect to a small change in 1 0 of layer 1, and rate of change of the cost function with respect to weight 1 1 of layer 1. And same thing, rate of change of the cost function with respect to a small change in the weight of the second neuron's weight coming from the 0th neuron of layer 1, and then rate of change of the cost function with respect to dw1 to 1. That's what we want to do, right? It is this term is saying that, okay, if I do a small change here, this particular term, just to like make people understand, I'm just taking one term randomly. This particular term here, rate of change of the cost function with respect to w12, is actually, it is saying that if I do a small change here on this term w211 here, how much this cost will change. Okay, now you don't have to go back up to this cost because you know the error up to this point. That's your advantage, right? It is same as now it is asking, it is asking now what this thing using chain rule. If you want, you can write it in this way: rate of change of the cost function with respect to up to z, how much the cost function changes with respect to dz2, sorry, here if you are computing this term here, how much the cost changes up to you want to compute now rate of change of this with respect to this particular term. You focus now this term you can write as rate of change of the cost function with respect to z of 0 d0 of layer 1. It means this z0 of layer 1, how much this cost changes with respect to z0 of layer 1, and that is actually this error here, okay, multiplied by how much this error changes, or how much the value of that g changes, d0 of layer 1 changes with respect to whatever the weight you're talking about, w01. So rate this thing with a small change with 0 0 of layer 1. That's what you want to compute. Okay, and that is multiplication, that is multiplication. And then this other term is whatever it is the rate of change of the cost function, or whatever the way this cost function changes with respect to this other term, 0 1 term. 0 1 term means, you see, the rate of change of the cost with respect to 0 1 weight. This 0 1 weight, it is same actually. It is whatever the cost function changes with respect to that z0 with respect to dz1 of dz0 of layer 1 multiplied by whatever that dz0 of layer 1 changes with respect to the weight 0 1 of layer 1. Okay, similarly you can very easily expand this thing to the other lines to, like, the other components, like dc of this term. Actually it is same. Now rate of change of the cost function with respect to 101, that means how much the cost function changes, how much this cost function changes if you do a small change in 101 in this particular weight here. Okay, so if you do a small change in this weight, so first you want to compute how much this cost changes with respect to this z1 1 here, which is nothing but the error accumulated at this point. Then how much that z11 changes with respect to this. Okay, the same thing. No, I guess by this time you have understood it. Okay, now how much this now z1 of layer 1, and then is z1 of layer 1, and then it is this w10 of layer 1. Okay, layer 1, and then it is rate of change of the cost with respect to this z1, the same term, same error, because you see for this one also the error is same, the same error. So z1 the same error, z1 of 1, and then these z1 of 1, and this is changed, this multiplied by the weight, whatever the weight we're talking about, 1 of layer 1. Similarly, this one is how much the cost changes with respect to dz2 of layer 1, and then how much this dz2 of layer 1 changes with respect to the weight with respect to this 20 weight, right? Okay, that is 20 of layer 1, and the same thing, rate of change of the cost function with respect to z2 of layer 1, the same error, z2 of layer 1, that is this point here, multiplied by whatever that dz2 of layer 1 changes with respect to the weight there. Okay, how much this thing is changing with respect to one weight, that is what we're going to compute. So with respect to dw21 of layer 1, yes, with respect to this particular one. Okay, that is, if I do a small change here, how much the cost changes. So how much the cost changes with respect to z2, and how much z2 changes if I do a small change in this weight there. Okay, now we know, like, this thing. Now let's now again do a copy paste. Now let's copy this matrix here. Okay, I just copied this same matrix from here to here so that we can have a clear view. Now what is this dc by d01, dc by dz1, and these are, as I said, no, these are, you can now write rate of change of the cost function. This cost function with respect to that z01 is, no matter what that thing is, it is the accumulated error at that point. So you can directly write, like, these are the accumulated error. So this dc, rate of change of the cost with respect to the z0 of layer 1 is nothing but it is the accumulated error at neuron 0 of layer 1 multiplied by this dz0 dg1. This term, let it be like that only. I'm just doing step by step instead of doing in a single go. Yes, I could have written it directly, but it's okay, no problem. And that's the fun of doing maths. Now same thing, dc dg1, these terms are same, so you just can write it like de0 of 1, which, and then this dz0 1, how much it changes with respect to dw011. Okay, same thing here, de, now it is the error at layer, the second neuron's error. So it is the error of the error of the neuron 1 of layer 1 multiplied by, this is also multiplication, don't get confused, multiplied by dg It is 0, huh? dz0. It is d1. dz1 of layer 1, how much that thing changes with respect to dw10 of layer 1. Okay, that is this second neuron. Just to verify it, see this one. We want to compute like this error multiplied by d101 and d111. Okay, d101, and then same thing. The other one is de1 of 1 multiplied by, because these two terms are same, multiplied by rate of change of this z value g1 1 with respect to the other weight. Other weight is dw11 of 1. Okay, and same thing, de2 of that error accumulated in third neuron then on of layer 1 multiplied by whatever it is the change on the temporary value of the third neuron, that is the z2 of layer 1 with respect to the weight of the third neuron coming from the 0th neuron of the previous layer, so of this. Okay, so that's what it is. And then whatever it is, this de2, that error accumulated in the third neuron, the same error multiplied by through the different weight now. So what is the different weight? Now whatever it is, this z function, z value 2 changes of layer 1 changes with respect to the other weight. So it is like the weight of the neuron 2 coming from neuron 1 of the previous layer, and neuron, this weight is w1. Okay, that's what w21 of 1. This is what ultimately we got this. Now only question left is, now since we know like d0 d1 d2 d0 d1 d2, we know that only thing left is now if we can do something about this. What are them? What are these? If we can figure it out, things are done. That's done. Now you know that will be over then. Now what is this? Let's concentrate on this particular term. Now we have to answer this question. Say what is dz0 of layer 1 with respect to dw100. Okay, that's what let's try to understand. So what it is asking you is that de0 of layer 1, dz0 of layer 1, it means z0 of layer 1, how much this is going to change if I do a small change in w00 of layer 1. If I do a small change here, w00 of layer 1, if I do a slight change here, then how much this is going to change? Got it? If I do a slight change here, how much this is going to change? Now by this time you should be able to answer me. Yes, no need to do any derivation. It is going to be proportional to the the input through which it is multiplied by, right? But then also let me like show only for once for those people who might not see. I know many of you will see it, but anyhow, let's come back to the point. What is this? What is this z0 and with respect to this particular one? And then if we want to do this, then we can like expand that z01. So what is z01 actually? You see this diagram, you see what is z01? It is the weighted sum of this one into this one plus this one into this one plus this b0. That's all, right? So let's write it. So it is this weight one of 0 multiplied by a0 of previous layer plus another weight is there, the same layer is weight 0 neuron only, but it is coming from the first neuron of the previous layer, so I have to multiply it with the first neurons of the previous layer. And then we have this bias term there, which is the bias 0 of layer 1. That's all. And you have seen me doing this quite a few times, so you now know is this rate of change of this. And then you want to do this, and then we know that only this 001 term is here only with this product. These two products are not going to change anything. I mean, they are not going to change with respect to this one, so they are all 0. So it is ultimately d, this is your constant, and this is this is your x now, and this is the constant. So dax by dx, so it is the constant, so constant is a0 0. So ultimately, what that term is doing, what this term is, rate of change of z0 with respect to w00 is a0. See, rate of change of this z with respect to w00 is a0 only, the weight through which it is multiplied with. Right now if it is the case, then what we can do is that we can now finalize these matrix then. So we can write this matrix as, now it is the error 0 1 term multiplied by z01 w01. It turned out to be the corresponding the neuron through which it is connected with of the previous layer. So it is a0 of previous layer is 0. So this, and what about this one? Here the error term is saying e01 and multiplied by how much this z0 changes with respect to 01. 01 means, see, it is the weight of the 0th neuron coming from the first neuron of the previous layer. So you can directly write it is the first neuron of the previous layer. Similarly, this term, this term is fixed, de11 multiplied by how much this z1 changes with respect to the with respect to the weight of the first neuron which comes from the first neuron of the previous layer. It is same. Now this thing is then a0, because you see this number here, it represents from which neuron of the previous layer it is, or to which neuron of the previous layer this weight is connected with, right? So this number tells you the neuron number of the previous layer. So directly you just by looking at this number you can write it. Okay, it is, since it is connected with the 0th neuron of the previous layer, so it must be proportional to the the value of the 0th neuron of the previous layer. Okay, similarly this thing is de11 multiplied by, now see how much this z1 changes with respect to the weight of the first neuron, that's this first one, which is coming from the first neuron, that is neuron at index 1 of the previous layer. So since it is coming from the neuron at index 1 of the previous layer, it will be proportional to the neuron, the value of the neuron 1 at this previous layer. Now it is same. Now de then 2 1, and if you see the symmetry, then directly you know what is this a00, because it is also this, see, this is the weight of the second neuron. Let's see this term for the final time. You see, we are computing how much this z2 is going to change if I do a small change in this particular weight. 2 means the second neuron's weight coming from the 0th neuron of the previous layer, right? And like it is if I do a small change here, the z2 is going to be changed, which will be proportional to this one, right? Okay, so that one is this a0, and then similarly it is de21 multiplied by a10. I just am copying it by looking at this term here. Okay, done. Then now if it is the case, now do you see something here? Now can we represent it as a, like, now these terms I'm doing like one by one element at a time, but can we compute? We have to compute this matrix. Now can we compute this matrix in a single go, but based on some previous result? And what you see here is that it is possible. And what is that thing is that it is same as the thing that we did previously, like you remember, it is, you remember like when we computed this weight matrix there. Just a second, this term here, you see, error multiplied by the activation of the previous layer, error multiplied by the activation of the previous layer, error multiplied by the activation of the previous layer, right? Now here you can see when we were computing the derivative of the weight matrix 2, weight matrix 2, there we had two errors. D is 0 of layer 2 and D1 of layer 2, and we had 3 activation from the previous layer, A01, A11 and A21. I mean this way, A21. Okay, so and what it was that we took the transpose of the previous layer's activation and we multiplied that thing with by the error of the second layer. See, we took the transpose of the activation of the first layer, then that transpose we keep on the right hand side, and on the left hand side we multiply it with the error to get this. The same thing it should be true here also if everything is fine. Now here blindly can we write it is now the error it is the error of layer 1 this time. Certainly it is the error of layer 1. See, error of layer 1. This time we have how many errors? This time we have 3 errors there. Layer 1 has 3 errors. Layer 1 has 3 errors, whereas layer 2 had 2 errors. But the other thing is again reverse. Now layer 2, like when we are propagating, we're trying to compute these the gradient of this weight matrix, then we had 2 errors and 3 previous neuron, but this time we have 3 errors and 2 previous neuron. Okay, that thing, I'm just mentioning that thing. But and ultimately what we want is that this error multiplied by following the same format. First let's write it blindly and then we'll verify whether it is true or false. Okay, but otherwise you can see the pattern here, or you can derive it. So D1, that is the error, multiplied by what we did is there's activation of the previous layer. Right now we are computing the the gradient of weight matrix of layer 1. So activation of the previous layer means activation 0. So activation of the previous layer is activation 0, and we have to take the transpose of it, right? And let's see whether it is true or not. Okay, so you see, if I do expand it, is E1, it will have 3 components. No, it will have like DE1 of 0, DE1 of 1, and DE1 2. These are 3 components we have. We have these 3 components there. This error vector, like it is a like 3 multiplied by 1 matrix, you can think it of, and then multiplied by a0. A0, we know it's a column vector. Column vector means a0 of 0 and a1 of 1, but we take the transpose of it, right? So this is equal to this. This is equal to, it is same as de0 1. I'm just expanding and showing you that ultimately we are going to get this one. I'm expanding, and at the end, if I expand it, I'll get it back to this one. Okay, so DE1 of 1 and DE2 1, same terms, and these matrix, the 3 cross 1 matrix multiplied by, this is transpose, I just want to write them right, A0 0 and then A1 of 0 at layer. This is a mistake here, I did 0 at layer, right? Okay, 0 at layer, and that's all. Now, if I expand it now, it is, see, what it is saying is that there will be 2 columns, certainly. Directly, there are 2 columns. And the first column is this much of this. That's all. That's the first element. D1, 0 of this A0, 0 is this first element. Done. Then D1, 1 into this is the second element. D1, 2 into A0 is the third element. And the same thing with respect to A1, 0, A0, 1. Okay, so if I expand this, I will get this. So it means this is equal to this. Okay, got it? Done. Then we have computed. We have computed this one also. What should be the changes in the weight matrix 1? And the changes turned out to be whatever it is the error in layer 1, multiplied by that thing with the transpose of the activation of layer 0, and then transpose. Okay, and then how to compute this DE1? We have seen DE1. We have seen how we can compute DE1. DE1 can be computed as DE1 can be computed as what? DE1 can be computed as this thing, DA1 into activation 1 of 1 Z1. Okay, but I'll summarize now. The next thing that is left is only to summarize all these formulas there. But then also let's see what we just have computed is the derivative of, or the by what amount we want to change this W1 matrix. Okay, and that's all. That was our final thing that we had to compute, right? Initially we decided what we had to compute, and step by step we computed everything. We did this, we saw how to compute this, how to compute this, and now we just have finished how to compute this one. Okay, now it's time just to summarize what are the those, how do we compute all this B and all. Okay, so okay, I'll first write it down and then I'll tell you. Okay, I have copied everything in the same place. Now we are ready to do that summarization. So we have this neural network where we have these two input layers, then we have a hidden layer, 3 neurons, output layer, 2 neurons are there, and this is how. Now I guess you know how to interpret these images. Now you see here, suppose we want to implement now this neural network, then what we do is first we assume like we have like one input vector. That input vector will change for each training example is an input vector actually. So we all these input vectors we have ready, and corresponding to that input whatever it is the output, that also we have actually. Okay, and you see here these here coincidentally the size of the input is same as the size of the output, but it might not match also. Okay, but one thing that we should know is that okay, this is the input vector and this is the corresponding output that we want. Okay, and then this neural network has in this intermediate layer we have a weight matrix that consists of all these weights. Okay, and what is the size of this weight matrix? In this case it is 3 cross 2, but if we have more number of neurons here, instead of suppose 3 neurons in this first layer, if we have 10 neurons in the first layer and 2 neurons in the second in the previous layer, input layer, then we would have it here like 10 cross 2. Okay, it just the size of that matrix depends on how many neurons you have in this layer. Okay, and then we have these biases also, like say for example for layer 1 we have this bias 0, bias 1 and bias 2. So that vector also we have, or that column vector, or you can consider that matrix also we have. And again it depends on how many neurons you have in that first layer. So this b1 represents the bias vector of first layer, so it has right now 3 neurons, so 3 3 biases. If it is like 10 neurons, it would have been like 10 cross 1. I mean the size of this vector would have been like 10 components there. Got it? So now you should realize this sizes doesn't matter, like you can decide any size and it will work. Okay, and then similarly this weight to matrix, then obviously whatever it is this its previous layers, its size, the size of this matrix depends on how many neurons you have in its previous layer, and then the next layer there. Okay, so we want the next layer to have 2 neurons, so 2 rows, and then previous layer has 3 columns, so 3 there. Okay, so and then this another bias vector is there, so you can see 2 neurons, so that's why this vector in this case it has the size 2 cross 1. But if you want your output vector to be say 10 neurons there, so it will have 10 cross 1. I guess the sizes will automatically, I guess if people appreciate the point that the sizes will automatically match if you do it in a sensible way. And this is your output vector. So initially if suppose you just assume now we want to implement a neural network, and then we have to first decide like how many neurons we want in the first, is it the input layer, how many neurons we have, how many neurons we want in the first layer, how many neurons we want in the output layer, that we have to decide. And once those are decided, we can declare these variables. See here, this is already available in terms of training example. This is again in terms of training example, but these weight matrix and this bias vector, we have to initially like assign to some random random numbers. That is, all these numbers will have this w00010101, all of them will have some random numbers. Okay, we'll initialize them with some random numbers. Done. So once those matrices we have and these column vectors we have, then what we do is we do a forward pass, and this forward pass boils down to be this few matrix operation. Now see here, what we do is we first compute this z0 vector, which is nothing but the this weight matrix multiplied by the activation of the first layer, that is the input, plus this bias, and then activation 1 is equal to pass this z through some activation function, whatever it is, that is a1. Then we compute z2, that is c. Once we compute a1, this vector, then we compute this intermediate result z2, I mean z of layer 2. Okay, so that is what z of layer 2, it is nothing but it is the weight matrix w2 multiplied by the activation of the previous layer, weight matrix w2, activation of layer 1, plus the biases of b2, plus this biases of b2, that is b2 there. Okay, and then whatever it is this z2, we pass it through some activation function, another activation function. I'm writing it as activation 2, and whatever it is, that is considered as the activation of layer 2. Since we have only 2 layers there, that activation of layer 2 will become the output, the output of the network. And then once we have this forward pass done, then what we do is we go to backward pass. That is, in the forward pass we compute up to this O0 and O1. And since we have this y also, then what we can do is now we can do the back propagation. So in back propagation, first what we do is we compute the gradients of all these different weights and biases. Okay, and for that sometimes we might be computing the gradients of some temporary result, which I marked here by circles, but our main point is to compute the gradient of the bias vector b2. That is, we have to compute the gradient of this b2 vector, we have to compute the gradient of this weight matrix, we have to compute the gradient of this b1 vector, and we have to compute the gradient of this weight matrix w1. So four terms, four different gradients we have to compute. Okay, that is this db2, gradient of bias vector at layer 2, gradient of weight matrix of layer 2, gradient of bias vector at layer 1, gradient of weight matrix at layer 1. And while computing, to compute say for example this db2 and dw2, we need this de2, which we say like, okay, this is the error at layer 2 on its neuron. That is this, we compute this intermediate vector de at layer 2, de2, which represents the error at its neuron in layer 2 or at layer 2. Okay, so that is this intermediate result, and using that intermediate result we compute like the gradient of b2 and gradient of w2, gradient of b2 and gradient of w2. Okay, and then again to compute the gradient of b1 and w1, we need to compute the gradient, we need to compute this intermediate result. This is error at this layer, and to compute the error, again we compute first the error at this point, and then we compute the error at this point. Okay, we're just doing it in two steps. So first we compute the error at this point, means we represent it by the error da1. It means the error at the the border of this the neuron of layer 1, and then once we pass that error, this is the error, and once we pass that error through the in some reverse order, like through the activation function, that we get the error at that particular neuron. It means at this point. Okay, and then from there these errors propagates back to its corresponding branches, like to b1 and to w1. All right, once these gradients are computed, then what we can do is we can update the weights. These are simple operations. Now the weight matrix w1 is equal to whatever the weight matrix w1 minus eta into dw1. This is a constant multiplied by the gradient of w1 vector, w1 matrix. Okay, the gradient of w1 matrix. So whatever the gradients we have computed for this, that gradient, some constant some proportion of that gradient, constant proportion of that gradient, will subtract from this weight matrix. Okay, and similarly we'll do the same thing. So whatever the gradient we have computed for these biases at layer 1, some constant proportion of those gradients will subtract from the the previous, or the previous. Actually, when I say previous means, so see, we do a forward pass, then when we're doing this backward pass, so whatever the biases we had in our forward pass, from those biases, that's what I mean by b1, from those biases we will subtract that constant constant proportion of the gradient of the biases at layer 1. And same thing, w2 equal to w2 minus eta into dw2, and b2 equal to b2 minus eta into db2. See there, these dw1, db1, dw2, db2, we all have these things are computed when we computed this gradient. See, dw1 we have computed dw1, and db1, this is db1, and this is dw2 is this dw2, and db2 is this db2. Okay, so this is a back propagation. Once this thing is done, once these operations are done, these are quite straightforward operation, isn't it? Once it is done, then we get a new weight matrix w1, new bias vector at layer 1, new weight matrix w2 for layer 2, and new bias vector b2 for layer 2. With these new weights and biases, see, now these weights and biases are now different from the initial random weights and biases. Now they are updated now. Now with these new weights and biases, then again what we do is we again repeat the same process. That is, again we do a forward pass. That is, with the new weights and biases, you compute these 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 intermediate result, and up to this the activation of the last layer, which becomes the output. And based on that output, we'll compute the gradient once again, and the gradients once computed, we'll update the weights and biases once again. And once these we get the new weights and biases, then we'll repeat this process. And how many times we usually repeat this process? It could be arbitrarily long, but that this repetition, that process is known as, like, epochs. Now see here, basically, epoch, how many times it will be repeated? Actually, epoch into the number of training example, actually, because you see here, right, we have assumed that we'll be updating the weights and biases for each training example. Okay, so for one training example, we'll be computing, see, we take the first training example, we'll compute this intermediate result, we'll compute the gradient, and then we'll update the weights and biases, and then we'll come back to this point, and then again we'll take the second example, and again we'll do this forward pass and this backward pass, take the third example, forward pass, backward pass. So in one epoch, we'll be doing it like for all the examples, we'll do this forward pass, backward pass, forward pass, backward pass for all examples in one epoch. And then we want to repeat the same process again, say as many epochs as we have. So basically, if we consider like in one forward pass and backward pass for each training example, if we do this, then total number of this forward and backward will be epoch into number of examples that we have in our training data. Now you might be thinking, like, if the training data has like millions of examples, then in each epoch basically we're doing it millions of times. Yes, that is true. If you go with this bare a very straightforward approach, that is true. But you can apply a slight trick there, that instead of like doing this, computing this back propagation for each of these input there, what you do is, we usually do what, we take a batches of inputs and we pass all these inputs in, we compute these gradients. We compute this, we do this forward pass for all these inputs together, then we compute the gradients for all those inputs, and then we update these weights, means as a whole, on average, we do that thing. See here, that is just a slight modification. You people do not need to worry much about it, because if you have understood up to this point, you have understood up most of the things, only whatever left is just some slight modification there on the top of the same idea. You just adjust, like, to you just rectify the same underlying concept so that it becomes more efficient. Okay, so that's all. Then this is the math of an artificial neural network. And as I said you previously, that this math will be quite beautiful, and everything will boil down to a few equations, and these are the few equations. In forward pass you do this, and then in backward pass you do this, and you repeat it a few numbers of time, and that's all. That's a neural network, actually. So once we know what is the math behind a neural network, and once we have this formula, in the next part of the video, what we'll do is, from this formula directly, we'll try to implement this formula, and we'll see using these formulas how you can construct a neural network from scratch. And when I say from scratch, I'll be using libraries like NumPy and all to do this matrix multiplication and all, but I'll not use any library which is specific to machine learning. Okay, so that machine learning part we'll be doing from scratch, but this matrix multiplication, computing the transpose and all, NumPy is like, really, I mean, if you don't allow me to use that NumPy, then I'll find it a bit boring to again write the code for matrix multiplication and all, from scratch. So that I don't consider from scratch. I just assume that matrix multiplication and all these things are there with NumPy, and using those the standard mathematical operation, will be implementing a neural network from scratch, and that will be the topic of the next video. Hope you people have enjoyed the video, and you have learned something from the video. If you like the video, please press the like button. It is very much important for me. And also please try to share these videos if you think this video is useful and you have learned something from this, and your friends also can learn something from this video. Please share this link with your friends, and that way my channel will grow. Okay guys, then that much only in this part of the video. See you guys with the new content in the next part of the video. Till then, have a nice day.